Okay, thank you so much. Uh, Let me briefly introduce myself. My name is Reza. I'm a PhD student at University of Queensland and working under supervision of Associate Professor Mehmet and Associate Professor Jivan. My presentation is designing hybrid micromobility system with integrated charging and rebalancing. This is my presentation outline. Why micromobility matters? It matters because it provides an efficient solution for short distance urban trips, on private cars, supports sustainable urban mobility goals, and improves first and last mile accessibility to public transport. There are some important concepts related to shared micromobility system. In terms of configuration, there are two main systems, a station-based system and free-floating system. Please look at the figure. Both zones have the buffer radius of 250 meters. So in the station-based system, user pick up micromobility devices from a station and drop them in the station. We have fixed location for pick up and drop off. And however, in free-floating system, micromobility devices are distributed within the zone. Based on this, we have some advantages and disadvantages for station-based system and free-floating system. In terms of station-based system, there are some disadvantages, such as long walking distance, capacity limitation, and high infrastructure costs, and there are some disadvantages. We are talking about the current station-based system with capability of charging pipes. So I can mention low charging costs, low rebalancing costs, and low maintenance costs. However, in free-floating system, there are some advantages, such as short walking distance, high capacity, low investment costs. And there are some disadvantages as well. I can mention high battery swapping costs, high rebalancing costs, high maintenance costs, and improper parking. Another concept is hybrid micromobility system. When we have a station and free-floating system, simultaneous work, this is called it is a hybrid system, and I provide two examples here. For example, paths one from A to F, user walk from A to B. B is a station, pick micromobility from a station and drop them in free-floating zone. Pick from a station and drop in a free-floating. Another is pick from free-floating zone, drop in a station and walk to reach their destination. Another concept is related to revenue. If you have a chance to utilize micromobility devices, you should pay unlock. And based on the time you have utilized and based on the distance you have utilized, you should pay another. This is a revenue for operator. And the concept is rebalancing. So there are two main rebalancing strategies in terms of time and in terms of implementation. In terms of time, there are two main strategies as well. The first one is static rebalancing, and the second is dynamic rebalancing. In static rebalancing, operator rebalance the system once per day, for example, overnight. And dynamic rebalancing, operator rebalance the system at the end of any time intervals to prepare system for the next time interval. In terms of implementation, we have user-based rebalancing and operator-based rebalancing. In user-based rebalancing, operator, by changing the origin and destination of user, rebalance the system by giving them incentives. And in operator-based system, operator needs to buy trucks and hire some workers to rebalance the system. For example, this is called a shortage zone because the number of users here is higher than the number of available micromobility devices here. And another zone is surplus zone because the number of available micromobility devices is higher than the number of users. So in this way, we can say, okay, this surplus zone. So operator should pick up extra micromobility devices from surplus zone and drop them in shortage zone. This is called rebalancing. So it is rebalancing and battery swapping is significant cost for operator. If I give you example, Bird's company in the US, spent over 40% of its revenue on rebalancing and battery swapping. So my motivation comes from here to proposing model to minimize the main contribution of our work. There were a few papers here, researchers propose hybrid system. All of them are single period. What I'm trying to say is that the location decision do not account for asymmetric demand patterns. And rebalancing is treated as a cost. In our proposed framework, we have hybrid system. It is time dependent. The location decision explicitly account for asymmetric demand patterns. We track the state of the charge of micromobility devices. Based on that, we can calculate the number of charging power in the station and the number of battery swapping costs in free-floating zone. And more importantly, rebalancing operation are explicitly modeled here. And we have simulation-based validation of optimization output here. Our objective function is minimizing investment costs and operational costs and maximizing revenue, subjected to walking distance, user-based, inventory flow constraint, rebalancing constraint, capacity constraint related to capacity of the station, trucks, and depot, energy balance constraint related to how to track the state of the charge. How we can calculate the walking distance here, as I provide one example here. Please consider we have a buffer radius of 250 meters. The average walking distance between user and the center of the zone, please consider 160 meters. The distance between the center of two adjacent zone is 500 meters. So user walk to the center of this zone. This is a station. We assume that the station is located at the center of any zone. So pick micromobility from station, drop in free floating zone. So the destination is free floating zone. So we don't have any extra walking distance because user can drop micromobility in its exact destination. At the end of the day, we can calculate the walking distance for this OD. We have considered here binary logit model. One mode is micromobility mode. In micromobility mode, we have considered walking distance cost. By increasing the walking distance cost, the probability of people utilizing micromobility decreases, revenue decreases. So this model keeps a balance between investment cost, operational cost, and walking distance as well. Instead of considering multimodal logit model, we just have consider other models. So it is the limitation of our work here. So we have a lot of mathematical formulas and constraints, but the most important one is related to inventory constraint. Based on this mathematical formulas or constraint, we can calculate the number of available micromobility devices in different time intervals, in different zone, and in different level state of the charge, based on the number of pickup, drop-off, inflow to a station and free-floating system from depot, and inflow to depot from a station and free-floating zone. This is example for rebalancing framework here. We have one depot and three free-floating system. Please consider this is a surplus zone with two extra micromobility devices. So depot go there, and truck goes there and pick up extra micromobility devices and back to depot and drop them in depot. So this is a shortage zone and pick extra micromobility devices from depot and drop them in shortage zone and back. So this is the rebalancing mechanism in our model, in strategic design problem. And we have considered movement between surplus zone and depot to shortage zone as well. And another constraint related to capacity of station, we have considered here 50 micromobility devices in the station. How to track a state of the charge? In time interval T, R is driving range of micromobility devices. K is the level state of the charge. We can start here. This is just example 10. It means that we split it over the 10. It means this OC between 0 and 10%, 10% and 20%. Please look at this figure and this example. The pickup node is A and drop-off node is E. So this micromobility has a battery state of the charge between 50% and 60%. We consider midpoint here. Based on the distance between origin and destination, we can calculate it, the state of the charge of micromobility peak from A and drop in E. So you can see at the level state of the charge from K6 reduced to K5. And we have another example here. At the end of the day, then the state of the charge of micromobility between 0 and 50%, and they drop in a, they can be charged in the station. So based on the number of micromobility devices dropping the station, simultaneously we can determine the number of charging pipe. And another issue is related to free floating zone. When the state of the charge between 0 and 20% and they drop in free floating zone, we change the battery of them and we can determine how many micromobility devices should be swapped here. We implemented in the 20 nodes of transportation network. This is solved by Groby, and we implemented the large network as well by utilizing the heuristic algorithm. You can see here comparison of the cell location and initial inventory. In a station-based system, free floating system, the same location, and hybrid system we have for station. And this figure shows revenue, investment cost, operational cost, and net value. For example, in station-based system, the investment cost is higher than free floating zone, it's higher than hybrid zone. And free floating zone, you can see here, operational cost is higher than station-based system, higher than hybrid system. At the end of the day, in hybrid system, the net value is higher than free floating system and station-based system. There are 3 different reasons for selection of a station and free floating zone. The first is capacity of station. Please look at the figure on the left. This figure is showing the number of inventories in different time intervals. And you can see node 2, node 5, node 14, and 19, all of them in free floating zone. You can see the number of inventory exceed the capacity of station. The capacity of station is 50. It is one reason. The second reason is walking distance, and the third reason is cost. The figure on the left showing rebalancing. I provide one example here. Please consider time interval 10. Node 2, blue one, the number of pickup in time interval 10 is more than 50, and the number of drop-off is less than 20, and we have shortage here, and you can see we have inflow to this zone from depot, and vice versa for another zone. The figure on the right, the first showing charging activity. The second, battery swapping in free floating zone. It's also distribution over the time. It's also transition between time intervals, and you can see micromobility devices that with that threshold drop in a station, and it can be charged, and we have just in time interval 9, we have just battery swapping. So you can see a hybrid system, partially eliminated battery swapping cost. Comparison, charging cost and battery swapping cost in optimization and simulation. We utilize the output of our optimization, the location of the station, free floating zone, the number of available micromobility devices assigned to the station and free floating zone, the number of charging pilot station. After that, we have simulation with our demand here. So you can see the charging in the station comparison between simulation and optimization in station-based systems near to each other. And we have a bit differences in free floating system, and we have a bit differences in hybrid system. At the end of the day, you can see by having some assumption in optimization, and you can see the operational cost, there is not a lot of differences between operational costs and operational costs in simulation and optimization, especially charging costs and battery swapping cost. This work was published in Parady. If you're interested, you can read this paper. Thank you so much. There are a lot of figures and there are a lot of results, but at the end of the day, there is not any time because of limitation of time. I cannot present. Thank you so much.
Okay. Thank you very much for maintaining the time. It's very important. So there is a question for you in the chat. If you stop the sharing, I think you can
Give
see
me a
it.
second, please.
So it says that in the hybrid system, how the difference between a fixed station and a free-floating zone is captured, and how is the capacity of a free-floating zone defined because there are no docks?
Okay, in free-floating system, we don't have any capacity. Just in that presentation slide, I just mentioned we have high capacity. We don't have any capacity in free-floating zone, but we have capacity in the station-based system. That capacity is 50 maximum devices.
Okay. And a related question, like it's not true that there is no capacity, right? Because there are special limitations in terms of the sidewalk. And I noticed that in many cities, for example, in Europe, they're starting to clamp down on the free floating system because it's an obstruction to the sidewalks, and they're trying to do some sort of geofencing. So you can't stop
Yeah,
it here. There's no rack, there's no dock, but there's still some limitations, right? So what do you think about that, and whether there is some way to incorporate this? I don't want to say virtual capacity, but some kind of space limitation.
yeah. Thank you so much. Yeah, it is. That's true.
But technically, there's no technical difficulty in assigning this, right?
Yeah.
Okay. Um, okay, so also that's a follow-up question. So is the capacity the only difference between the two type of station zones?
Now all of them are the same here. All of
But
the same.
no, I think that they mean in terms of a free-floating zone and a station zone, the only difference is that one has capacity and one doesn't. Or in the formulation of the problem, there are other differences.
There is not any differences in capacity. We don't consider any capacity or limitation, capacity limitation for free floating zone. If you mean capacity for different stations, we don't have all of them are the same in the network.
No,
For
I think the question
example,
is if the difference between a station and a free floating zone is that the one has capacity and the one does not have capacity.
yes,
Okay.
yes,
So
yes,
any
yes,
other
yeah,
setting are the same.
yeah.
Oh, okay, I see. Thank you. Um, okay, I think they are clear. So if there are no other questions, then we're right on time. So I would like to wrap it up here. Thank you very much, Reza.
Thank you so much. Thank you so much for participating.
Then we're gonna move on to the first presenter now. So can the first presenter share his slides?
Yeah, sure. So
And
I'm sharing my slides here.
please go ahead. And a reminder, two things. Let's keep up the time because we are limited. We only have 15 minutes. And
Okay.
you can ask your questions on the chat whenever you're ready.
So can you see my screen here?
Yes. Can you switch
Okay.
it to? Okay, perfect. Go.
Okay. So hello everyone. So sorry for the delay. So today I'm going to present my work with my supervisor Yuen and Szeto on repositioning in bike sharing systems with broken bikes, considering on-site repairs. So the bike sharing systems, as the previous presenter may have already mentioned, requires effective repositioning. So we consider this scenario where three users are going to rent bikes in these three stations. So uh, currently, like for station one, this user, there are three usable bikes here, and this is a surplus station. And for station three, there's no bikes available, but three users are renting bikes here. So what we want to do is move those additional surplus bikes from other stations to this station. So this process is known as bike repositioning problem. And there's a more complicated case where like these two bikes become broken. So now after this bikes has been moved to station three, originally it is fine because this user still have two bikes available, but now the user has to leave and may cause the abandonment of the usage of the system. So and according to the City Bike monthly report, like the problem of broken bikes is non-negligible. It has the number of broken bikes or the number of repairs conducted as rising from 74,000 to now in 2022 is climbing to like 600,000. So conventionally, what we known is like we send all the broken bikes to the depot for the consistent or uniform repairs. This is called off-site repairs. However, in real cases, as we know, like there are some on-site repairs where those repairers just fix the bikes on-site with some like minor problems of those bikes, and these bikes becomes usable at once, like in 5 minutes or 10 minutes. So, and we all know that repositioning schemes with long routes or heavy vehicle loads, in this case, is the heavy bike load, may produce more carbon emissions, while the launch of the bike sharing scheme is to reduce the carbon emission. So this is against the intention of this bike sharing system. So incorporating on-site repairs could alleviate this problem. So formally, we talk about this problem. So in our cases, we have a fleet of vehicles that travels around across the stations, and also simultaneously there is a set of fleet of the repairers travel also in the same network. So they depart from and return to the depot, and we give every agent, like every truck and every repairer, a same time budget. So every truck can visit any station arbitrary number of times, and every station can be visited by at most one repairer at once, because there's no point that a repairer come to one station like twice or more times. And this is the number of bikes loaded or unloaded at every station. And also, we need to differentiate between the number of usable bikes and the number of broken bikes. So those broken bikes can still be carried back to depot, but some of them can just directly be fixed on-site by the repairers. Okay, so like classic arc index formulation is unable to handle this because we allow an arbitrary number of visits to a station, and we need to keep track of a station being visited by both trucks or repairers to know the up-to-date number of usable bikes or broken bikes when a repairer or a truck come to a station to determine the inventory of broken bikes and usable bikes. So we use this IJTK as the decision variables. So these are the two key decision variables, and they are binary variables to determine the visits of the trucks and the visits of the repairers. And these decision variables are the number of bikes being carried or delivered to a station, and the number of bikes being repaired by a repairer. And each follow a period T to keep track of the time. So this is the objective. So basically it's in two parts. The first one is the user dissatisfaction given consequent usable bike inventory and broken bike inventory at the station after the repositioning. And the second one is the carbon emission. It is calculated like this, and the key factors are the travel distance D and the loads of bikes on truck. So this is consistent as what we know in the introduction. So we use the two penalty cost for the two terms. One is the user lost cost, and the other one is the carbon emission cost. And in terms of the user dissatisfaction, it is calculated based on a prestigious paper in IISA published in 2017. So basically, we use a Markov process to determine the number of occurrences of a user failing to rent or return a bike. So we calculate the expectation. So this is the probability of the transition of the inventory during a day given a time period. So we calculate this expectation to measure the number of occurrences of the failure, rent, or return behaviors, so that we can calculate this for every station and given every inventory. So this is different from many conventional paper. In those papers, they set a target inventory and they try to minimize the deviation of the current inventory to the target inventory, which they treat this as a linear problem, and also they're treating every station as the same station, which is also not reasonable. Like a station in the urban or rural areas must be different from the stations like near the subway stations in the city center. So, however, this is a nonlinear problem, nonlinear objective function, and we need to linearize it. And a convex polyhedral function can be used in the MILP model, so that it has the nearly identical values to the EUDF in our objective function, so that this problem can be solved using like the modern commercial solvers. So the problem is NP hard. Like originally it is already NP hard. Now we consider both repairers and trucks, and we use time index formulation. So for small scales, it can be solved with Groby, but for large scales, we use the heuristic. And here we use a hybrid search, adaptive diversity control, and a station budget constraint heuristic. So I'm not going to detail of this algorithm, but I just want to mention that the outstanding part of this algorithm is it keeps both feasible and infeasible solutions. And also it managed the diversity of the solution rather than just the objective value. So it has been successfully applied on similar studies, like a multi-type bike repositioning paper published in 2016. So the next thing I want to mention is the innovation of our algorithm design in this paper. So traditionally, what we are searching is the route, and after the route is given, we need to assign the number of bikes loaded or unloaded at each station. So traditionally, we use greedy heuristic. That is, we use this minimize function to carry or deliver as much bikes as possible, given the truck capacity constraint, given the deviation of every station, and given the time budget limitation. But this has a problem that in this way, you just assign the quantities station by station along the route. It should only give time and capacity resources prioritized to the station that appears in the front of the route. However, this is the user dissatisfaction heat map. Like for some stations, like for the third station, you see when you move 41 bikes, like 20 usable and 21 broken, you got a reduction in the user dissatisfaction from around 8 to 0.83. However, like for the nearly same variation of broken bikes in station 2, you could reduce it from 100 to 18. So this is different. So this sensitivity to the number of bikes on the EUDF is different across the stations. So efforts should be prioritized to the stations that is more sensitive. In this case, it's like station 2 rather than station 3 when we assign those resources. So we defined a benefit over cost ratio function to measure this sensitivity, and we assign our time budget to every station to set a cap on the time budget that you can spend at every station proportionally to this BCRF. So rather than the remaining time, we replace this to station budget so that the front stations won't use up every resources if they're not important. So this is the result. So on small cases, we see like for one case in 10 station instance, Ruby takes like around over 13,000 seconds and to achieve the optimal solution. While in our algorithm, we use only 3 seconds to achieve the same objective function. And for larger cases, like when we increase the time budget, here the time budget is not related, it's not talking about the time budget, the computational time budget is the time budget we assign to the problem. And the computational time budget is still 2 hours in this case. And we see all our Groovy result, all our algorithm results achieves large gaps comparing to the result given by Groovy in 2 hours. When we increase the size of the stations for large cases, like over 200 stations to 500 stations, we see that Groovy is running out of memories, so we cannot obtain any feasible solution in this case. But our algorithm still outperforms all those results obtained by Groovy. And finally, we conducted a effectiveness of the repair times. So we use a cost effectiveness variation to investigate whether incorporating one repairer to the system is cost effective. So the red point means longer repair times makes it unworthy to introduce a repairer. That is, the cost effectiveness is below. At the left side of this red point means incorporating one repairer would be cost ineffective. Like in the right-hand side means it is cost effective. And so to summarize, we propose a new problem of bike repositioning problems with broken bikes and considering on-site repairs. And we gave a time-indexed formulation and developed a new algorithm. And we observed that the cost effectiveness of involving one repairer decrease with longer repair times, and the larger broken bike inventory delays the point when it becomes cost ineffective. So there are some ongoing research, like we differentiate the broken bike types based on the degree of damage, because some bikes are largely or seriously damaged and they cannot be repaired on site. And also we consider to use like dynamic deployment of repairers based on the system status. So that concludes my presentation. Thank you. And questions are.
Thank you very much. Yes, so I will exhort the other participants to post their questions on the chat, but if you can close the sharing screen, you can probably see the questions. They're my questions. So you mentioned the dissatisfaction measure, right? And you put that plot where you can change the same number of bicycles and the results would change by station. So can you elaborate a little bit on what exactly goes into this dissatisfaction measure and what makes the values different across stations?
Okay, so then I have to share it again, sorry.
Yeah, it's okay.
Yeah. So okay, so this is the transition graph of the two inventories, and this lambda t is the rent, and mu t here is the return rate of a bike. So we use this transition graph to calculate a transition rate matrix, and using this transition rate matrix, so the phi here means the probability a user rent a usable bikes but return it broken. So in this case, if you the 1 minus phi means it's not broken, so it rent a bike successfully. So the number of usable bikes increase 1 from 0, 0 to 1, 0. And in other case, it returns a broken bike here. So the number of broken bikes becomes 1 here. So we use this transition graph to calculate the transition rate matrix, and we calculate the transition probability matrix. So here that from pi, So like this 35206 from t equals to 0 and to t equals to 2 means we have a transition from 3 usable bytes and 5 broken bytes to 0 usable bytes and 6 broken bytes at period t. So in this probability expectation, we traverse all the possible inventories combinations given one station from the initial inventory to the so this case means 0K here means there is no usable bikes available. So the user may have a failure to rent a bike. And the second part is, so C minus K to K means the station now has C. C is the capacity of the station. So means the station is full and the user cannot return a bike. So mu and lambda T here corresponds to the rent and return behavior of a user. So this calculation just calculate the expectation of the occurrences of the user being unable to rent a bike or return a bike. So this is the EUDF.
Okay. Are you considering the demand of that particular station in that case? So the probability that I
So
would
this
go there
mu t, I believe the demand is in this mu t and lambda t. These two numbers are calculated based on the historical rent and return data of the city bikes. Yes.
Okay, I understand. Thank you. And okay, so there's another question, so a follow-up as well. You mentioned it at the end, so I was curious, like, how do you know? Because you mentioned that sometimes you will not be able to repair the bicycle on site, right? Because it's too complex, whatever.
Yes.
So do you have a distribution, or do you have historical information about the damage of the bicycles, or you assume it's just random?
So currently not included in this paper, but now like in China, like in those I believe the problem is mainly on the data acquisition. So we don't have this, but in China now, in many bike sharing apps, the users can actively report where the bike is broken, like it is the rack or the bells or the tires or something. And they can, but this still requires manual collection. And I don't know whether we can obtain this kind of data. So yeah.
Okay, I see. Thank you. Very interesting.
Yes.
Is there any other question for this presenter? You have a couple of minutes. Okay, so if there are no more questions, then I would like to wrap it up here, but feel free to ask questions to any other presenters in the chat during the session. Thank you very much. So we'd like to move on to the third presenter, Mingxuan Chen, talking about e-bike repositioning problem with charging and non-charging docks. So whenever you're ready, please go ahead.
Testing. Can you hear me?
Yes, I can hear you.
Thank you. Let me share my screen now. Just a minute. Can you see the slides?
Yes, I can see it.
Good. Thank you. Then thank you for coming to this session, and good morning or perhaps afternoon, evening, night at your place. Today I'm going to talk about this e-bike repositioning problem with charging and non-charging docks. The background is still in the bike sharing systems with bike repositioning, as thanks to Reza and Runqiu, they have introduced the concept of bike repositioning. And in this problem, we also incorporated the shared e-bike. And for shared e-bike, there's a unique challenge, which is the recharging problem. This has been handled by either battery swap or on vehicle charging, or like using the charging docks. And the focus of this study will be on the charging stations, with part of it being charging docks and part of it being non-charging docks. And later, I'm going to show the model together with the loading, unloading, and moving subproblem, followed by the numerical experiments with sensitivity analysis on the percentage of charging docks and also the repositioning time budget. and also the hybrid genetic search with 3 heuristics introduced. So, sorry, okay. So I'm just going to play the animation because it has been introduced by the first 2 presenters. So in a sharing system, the user can just ride a bike to another station and return it over there. So sometimes things could go wrong because some station may be in surplus like station B or in deficit like station A. And what bike repositioning do is to hire perhaps a truck to carry the bikes from the surplus station to the deficit station. And as you can see from the previous process, bike repositioning problem typically include a routing problem, which determine the order of the stations to visit, and also a loading or unloading subproblem, determining the number of bikes to load or unload at each station. And here you can see on the photo on the left-hand side, there are some shared e-bikes offered by the operators in recent years. And compared with conventional bikes, the e-bikes, with the aid of the motors, e-bikes travel faster, and they can also reduce the fatigue of riding, especially for upward slopes. And some operators, they even only provide e-bikes as the only choice for their customers. And as mentioned, a unique challenge for e-bike is the charging problem. So unlike conventional shared bikes, the e-bikes need to be recharged when the battery is depleted. So one way is to do the battery swapping. For example, on the left-hand side, there could be some battery cabinets in the system, and then the truck can traverse between the cabinet and an individual bike nodes to swap the battery for depleted bikes. And the other alternative is to use a charging dock. So for example, here, when the e-bike is parked at a station, it can be charged by the charging facility over there. Another example in Hong Kong is this operator called Local Bike. So they once published this tweet about the wireless recharging station using the solar energy. And for the problem description, we have some assumptions such as each vehicle departs from the depot at most once. Each station is visited at most once by at most 1 vehicle, and the vehicle can carry loads when leaving or returning to the depot. The capacity cannot be exceeded, and e-bikes are categorized as either usable or unusable based on the battery level. Docks are categorized as either charging or non-charging docks. And the objective is to minimize the weighted sum of the total penalty value and the total travel, loading, unloading, and moving time. So here's a example of what could happen at a station. So here we consider an example with 1 green colored, the usable e-bike, and 3 depleted unusable e-bike denoted in red. And at a station, there are 2 charging docks with a lightning mark and 3 non-charging docks. So how can we recharge the e-bikes at this station? The first way is to move the unusable e-bike to a charging dock. Afterwards, because now 1 charging dock is occupied by usable e-bike, so we can vacate it by swapping the usable e-bike to a non-charging dock and then move a unusable e-bike to that charging dock. Afterwards, now all the charging docks are occupied by the unusable e-bikes. So what we can do else is to just move this unusable e-bike on the truck and perhaps move it to somewhere else for recharging. And at the end of these operations, after these 2 unusable e-bikes is recharged, we will have 3 effective usable e-bike at the station. So here's the model. The first term is the total penalty. So we use the same concept as in Runqiu's study. So the EUDF, which I will also show an example later. And the second term is the weighted total travel and service time. One of the popular ways to solve this problem is to separate the routing part and the loading and unloading part. And this TV, the travel part, is affected by the routing decisions. So if we separate from the problem, then we can extract the loading, unloading, moving subproblem. So the first term is still the penalty, and the second term here is defined by this constraint. So it includes the loading and unloading time and also the moving time. So here, as mentioned, this the same study in 2017, this penalty function. And suppose we have a station with capacity equal to 8, there will be 45 combinations of usable and unusable e-bike at the station. So let's think about a case with the number of usable e-bike fixed. Then with the increment of the unusable e-bike, the penalty value will be monotonically increasing. And with the number of unusable e-bike fixed, then with the increment of the usable e-bike, the penalty will show a convex pattern. And follow this direction. So the total number of usable and unusable e-bike is the same. But then with the total number being the same, with the increment of unusable e-bike, still the penalty value shows a monotonically increasing pattern. And we can show an abstraction of the triangular table on the left-hand side in the triangle on the right-hand side. So here we have 3 probably beneficial actions to decrease the penalty value at the station. And you can see they can be depicted by the arrows A, B, and C here. And the dotted blue line shows the target value at different number of usable e-bike at the station. So the target is to arrive at the optimal penalty value, which is 30, and the penalty value is 3.59 here. So later we were going to use this abstraction to show the rationale of the heuristics. And as mentioned, we have designed 3 heuristics for the problem. The first one is about forward greedy, which means that we only consider current station and consider from the first station until the end of the station on the tour. So here, let's consider, supposingly we arrive at station 4, then on a vehicle, supposing there are 6 unusable e-bikes. So what we can do here is that using the remaining so currently at the station, there are 2 vacant charging docks and 4 unusable e-bikes. So the first way is to move 2 unusable e-bike to the charging dock, and then we can load the 2 unusable e-bike on the vehicle. And then so it's still possible to load 2 usable e-bike and unload it at station 4. So in that way, we can move from the black dot, the initial inventory level, to the optimal target. However, this could lead to some myopic operations. For example, at station 6, the vehicle has been filled with unusable e-bike. Although station 6 needs some more usable e-bike to be filled at the station, but now nothing can be done over there. So this yellow arrow shows what could have been done at station 6 if there are enough capacity on the vehicle, but now we cannot do anything over there. And the second heuristic is the backward with exchange. So backward means that we consider loading quantity from backward to forward on the route. By using this approach, we know the information of the following stations when considering the current station, and this will enable the exchange move I'm going to explain now. So now the vehicle can just load 4 unusable e-bike from station 4, and this will be the effect of the penalty value at the station, the green arrow. And then at station 5, what the vehicle can do is that it can load the 4 usable e-bikes from the charging docks at the station, and then unload the unusable e-bike loaded from station 4 to station 5. Afterwards, the loaded usable e-bike from station 5 can be used to supply the deficit at station 6. So what happened at station 5 is called the exchange operation. This is because we know the information of the following stations when we consider the loading quantity. And heuristic 3 made a further improvement, which is to make use of the convexity of the penalty function. So for example, considering station A and station A+1. So if we load 1 more bike from station A and unload it to station A+1, so there could be a considerable reduction of penalty value at station A at the cost of a small increment of the penalty value at station A+1. So here, if we do not consider any buffer, then station 5 and station 6 are already balanced. So basically nothing can be done at these 2 stations. But if we enable this buffer, what we can do is that we can make some loading and unloading operations at these stations, and then the penalty at station 4 will be considerably reduced at the cost of a small increment of the penalty at station 5 and 6. And for the routing part, it is solved by hybrid genetic search using the paradigm in this study. And for some sensitivity analysis for the percentage of charging dock, we can see that with the increment of the percentage of charging dock, the marginal benefits show a diminishing pattern, and also a small proportion could already make a big difference compared to not equipping any charging docks at station. And for repositioning time budget, if we compare the blue line showing there are 15% of charging docks and the yellow line showing that there are 25% of charging dock. So if we only give 2 hours, 7,200 seconds for repositioning, when there are 25% of charging docks, it can only achieve the same result as if we only have 15% of charging docks. So what this tells us is that a sufficient time budget is important for exploiting the charging docks at the stations. And for the numerical experiment of the heuristics, so for small to medium networks, for most of the cases, the heuristics with the hybrid genetic search with the heuristic embedded can get the same result. Well, for larger networks, so one pattern can be observed here is that for when there are fewer vehicles in the fleet, then the hybrid genetic search with the second heuristic embedded tend to outperform. While there are more vehicles in the fleet, then the hybrid genetic search with the third heuristic embedded so tend to outperform. In summary, this was a study about e-bike repositioning problem with both charging and non-charging dock at the station. And in terms of the sensitivity analysis, a small proportion of charging docks can make a considerable reduction in the objective value. And also sufficient repositioning time is important for exploiting the charging docks. And we have also introduced 3 heuristics for solving this problem. Here are the references, and thank you for listening. This is the end of the presentation, and questions are welcome.
Thank you very much. I have 1, 2 questions in the chat. If you can stop sharing, you can say them, but
Sure.
I can also read them. So my question is, like, in the actual Chinese market, do you know what is the ratio between charging and non-charging ports? Or do you think the Chinese market is moving towards a full e-bike model, or any insights on that?
Well, thank you for the question. I do not really have a supported data of like the ratio of charging and non-charging ports. What I read from the previous study is that so normally they would consider a place explicitly for charging, like the bikes, the e-bikes can be moved to that place for charging as a central station for charging.
Yeah.
But a scenario here is that how about we move some charging facilities to the docking stations and make part of it as a charging docks, and the other remain as non-charging docks.
Okay.
I don't really have a real world example of this scenario, but it could happen in the future. And for the Chinese market moving towards a full e-bike model, I still think that the conventional e-bike so some people may still prefer the conventional e-bike, although
when you say conventional bike.
Conventional bike, yeah, sorry.
Okay, so not electrified, okay.
Yeah. This is the optimal or ideal ratio from the operator's point of view. This can be done by I think this can be done with a combined research with both station design and repositioning design. So this in the current study, we only focus on the repositioning part, but it can be incorporated in a station design problem. Like we can set the ratio of charging docks as a decision variable and see how that would affect the from the operator point of view, maybe the profit of the operator, and which is how we can achieve it, like the cost effectiveness of setting the ratio of the charging docks.
Okay, because what you mentioned was that even a small number increasing actually has a big effect, and then you have the marginal diminishing returns, right? So the optimal thing is not to have everything charging, but just a small amount. So identifying that, I think, is very interesting from the perspective of the operator, right? To be able to maximize their profit.
Yeah, exactly.
Very interesting. And then you have a question from Reza. So is the main objective of moving from the low SOC device between stations to reduce battery swapping requirements, or are these movements also treated as part of the rebalancing operation?
Yes. So we have a moving time to capture the operation time for this kind of operation. Like at a station, so now there could be several types of operations, such as loading the usable or unusable e-bike on the truck, or unload the usable and unusable e-bike from the truck, and we can move the unusable e-bike to the charging dock, or move the usable e-bike from the charging dock to the non-charging dock. So these operations are considered in the rebalancing operation, and the time is also blocked. So we'll consider the service time, including both loading, unloading, and also the moving operations.
Okay, thank you very much. Are there any other questions?
Thank you.
Okay, so it seems there are no more questions, but again, a reminder, you can ask any question to any of the presenters during the duration of the session in the chat. So feel free to do so. And then I would like to move to the next presenter regarding build environment impacts on zonal shared e-scooter expenses, a Bayesian learning approach. So whenever you're ready.
Okay. Wait a minute. Hi, can you see the screen?
Yes, go ahead.
Okay, good morning, everyone. My name is Wang Ruigan, a master student from Southwest Jiaotong University. Today, I will present our study about relationship between the built environment and the zonal shared e-scooter expense. Instead of focusing only on trip counts, our study asks a more practical question. Where is the operator revenue actually generated? To answer this, we combine log-normal regression with the Bayesian and regression tree to capture the skewed distribution of expense and the nonlinear effect of built environment factors. Shared e-scooters have become a popular micromobility mode in many cities. Most previous e-scooter studies focus on ridership and ask how many trips occur in each area. However, trip count alone doesn't fully represent the economic value of these trips. In this study, we shift from our ridership perspective to an economic perspective. We examine zonal trip expense, which captures not only trip frequency, also trip duration. This is to ask a more practical question: where is e-scooter expenditure actually generated? Our data sets are from Chicago 2019 e-scooter pilot program, running from June 15th to October 15th. We select this case because the pilot program provides fine-grained trip records at the census tract level, which become community level in later years. The raw data include 700,000 trip records. After filtering out trip with unrealistic speed, distance, and duration, we obtain about 560,000 valid trips across 249 census tracts. Since real-world fare information is not directly provided, we estimate trip expense based on the standard pricing scheme back then, a $1 unlock fee plus 15 cents per minute. Expenses are aggregated by trip origin and normalized by tracked area. Our expenditure variable, 16 built environment indicators in total, are obtained from the smart location database. They fall into three groups: transportation infrastructure, land use attributes, and social demographic. we use log normal plus BART to tackle two key challenges. First, the log normal likelihood handles this right-skewed expense distribution, as you can see from the histogram. Second, BART flexibly capture complex nonlinear relationships such as threshold and the plateau effect between built environment predictors and the trip expense. We evaluate predictive performance use mean absolute error, root mean square error, and R square, and interpret the model using variable importance and the partial dependence clause. Our model comparison demonstrates that log normal plus BART yield the best performance compared with the standard BART. This confirms that accounting for right-skewed expense distribution greatly improves prediction accuracy. Now, moving to variable importance, medium income and the POI density rank as the top two predictors. They are for shared of POI density, white residents, and the distance to CBD. Broadly, social, economic, and the land use factor play a larger role than transportation infrastructure variables. Variable importance tell us nothing about the direction or nonlinear shape of effects. So we further investigate this relationship using the PD. Now let's look at our key partial dependent results. First, for medium income, predict trip expense goes up gently at low to moderate income, then rise sharply for high income tracts. Second, as the POI density grows, expense increase rapidly at first before showing diminishing marginal returns and starting to plateau. More POIs do not keep bringing proportional gains. Third, predicted expense fall as distance to CBD increase. Even though our study area excludes the CBD itself, urban centrality still matters for revenue generation. The shaded band around each curve show our model uncertainty. Now we visualize these patterns with two maps. On the left, estimated fare expenses clusters in the eastern pilot area near the CBD. These high revenue tracts correspond to higher income and POI dense neighborhoods. On the right, we look at the share of car-free household, which represents mobility needs. Notice that many tracts with a large car-free population, especially in the southwest, have lower escorter trip expense. This didn't mean that they have little travel demand. It should reflect of affordability limit or people using other transport options. To sum up, commercial revenue potential and the real-world mobility need do not fully overlap. This finding leads to different implications for operators and urban planners. For operators, estimate expense are potentially is higher in relative high income, POI dense, and the central located area. However, because the POI effect plateaus, concentrating additional scooters in the dense zone may generate diminishing returns. The positive association with bus stops and the DV facilities also suggests opportunities for coordinated multimodal deployment, although this relationship shouldn't be interpreted as casual. For planners, some car-free and low-income area may have substantial mobility needs, despite relative low expenditure. Target subsidized rebalancing program and a safer infrastructure could help address this gap. Our work shifted the micromobility research beyond simply ridership counts toward trip-level fare expenditure. Our log normal BART model jointly addresses skewed economic outcome and the complex nonlinear built environment relationship. That said, this study has clear limitation. First, our evidence comes only from one Chicago program, so generalizability is limited. Second, model estimated trip expense instead of real operator revenue data. Third, while we identify key associations, we cannot draw causal conclusion. Overall, shared mobility is simultaneously an economic geography and an equity challenge. Thank you. That's all.
Thank you very much. You still have like 5 minutes. Is it okay? Actually more. Okay, so the questions are in the chat. You can look at them. The first one is, so you're estimating essentially by distance, right? So you're trying to predict how much people will travel based on different attributes. So how different do you think your model estimates will be compared to a simpler model that only focuses on, let's say, trip frequency and average revenue? Because your main premise was that you want to move away just from ridership, right? But you can multiply ridership by an average trip revenue, you get a rough estimate. So how much better is your prediction compared to this simpler model?
Yes, previous work used the ridership as a dependent variable, and we use the trip expense. Trip expense is a variable more concern about the economic. So it focuses on one hand the operators, the profit they can generate, and on the other hand, for the government, the equity, it can show these two constraints. So we use the trip expense as our dependent variable. Thank you.
Yeah, but so my question is, if you were to use a simpler model that just uses ridership and average trip revenue, how much better would your model be? That's the question I'm asking. Like, do you think your model improves considerably the prediction of revenue, or that would be a good comparison in terms of what it is worth it to invest in actually a more complex model, right?
What is worth it to invest in a more complex model? You means we change our do you means we change our dependent variable? How many accuracy we improve?
Yeah, I mean, exactly. Not dependent variable. If you use a simpler model that doesn't focuses on the distance of the trip, just average trip revenue and ridership, how much worse would that model be? Because the point of your model is you want to focus on more accurate estimation of profit, right, or revenue. So compared to the simpler model, how much better your estimates will be? That's my question. You don't have to answer now, but I think if you do publish it somewhere else, it'll be interesting to do that comparison against the models that are already in the literature.
Oh, okay. Okay, thank you.
And then the second question is about you mentioned in the end the policymaker, I mean the equity gap, right? So the operators want to maximize profit. So how do you think, Paul, can you elaborate a little bit more on what kind of policies can be implemented to fill this equity gap?
You mean how to fill the equity gaps, right?
Yes.
Operator, because we have examined many variables like car-free household, and our dependent variable is also concerned about the economic, highly related variables about the equity. So we found the these two these two variables didn't overlap in the same map. So many areas in the high car-free household, they may have much more potential to use this micro mode, but for economic reasons, they have not much more money to use it. So for the operator or for the government, maybe they can make more measures to let these people with a lower income or higher car fleet to use more e-scooters, like give them coupons or any other methods.
Okay, thank you. Are there any other questions regarding this presentation? Okay, if there are no more questions, it's a bit early, but I would like to wrap it up here. Thank you very much. And then a reminder that you can still ask questions in the chat to any of the presenters. I can see that there is some discussion going on. Thank you very much.
Okay, thank you.
So we're a little bit early on time, but I will be presenting now about the mitigation potential of micromobility across different countries. Second here. Can you confirm if we're looking at the right screen or are you looking at the presenter screen?
Seems as the presenters.
The presenter screen?
So
Okay.
we can see the notes actually.
Yeah, okay. So maybe what about now?
Oh, it should be fine. Thank you.
Okay, wait, actually I don't need, there's no notes. There you go. You can see the full screen now, right?
Yes, yes.
Okay. So thank you very much. My name is Giancarlos Parady from the University of Tokyo, and I'll be talking about the climate mitigation potential of micromobility. It's first now, okay. Wait, give me a second. I cannot switch for some reason. Let's try to do that again. Take that again. So are we in the right screen now or still inverted?
It's full screen.
Yes.
It's full screen? Okay.
Yes.
Okay, so sorry about that. I will be talking about international comparison of climate mitigation potential of micromobility. So as a motivation of the problem, we know the transportation sector is the fourth largest emitting sector in terms of carbon emissions. So there is a strong necessity to reduce these emissions. And most of the emissions actually come from road transportation. So switching to an EV fleet, electric vehicle fleet, is an important and essential step. But there is also this large share of emissions that can be avoided because they are theoretically addressable because they're actually very short trips. So there's a lot of trips that are actually under 5 kilometers. So theoretically, this could be addressed via micromobilities. And while you look at the global environmental assessments like the IPCC reports, these usually do not consider micromobility because the scale is just not the same. And when we say micromobility, we're referring to vehicles that are light, so under 35 kilograms, and usually have speeds under 45 kilometers. So these kind of mobilities, as you probably are aware, are used for shorter trips between under 5 kilometers, between 10 and 20 minutes. and also have a first mile, last mile role. But they also have, when you look at shared fleets, they have a lower utilization rate, so 1 to 2 trips per day, which usually results in weaker life cycle benefits compared to private devices that have actually a higher use and a longer lifetime. So in that sense, the research question that we want to answer here is to what extent can micromobility contribute to global net zero targets by 2050? And in the analysis that we're presenting today, we are presenting a harmonized quantification of micromobility mitigation potential by 2050, considering different vehicle technologies deployed at the ownership or different operational models. We move the evidence base from single city and single country or single technology to a comparison of many technologies and also different regions with different characteristics, and we provide a full life cycle assessment. So our analytical framework has two main components. So the first is the behavioral component that essentially estimates how many kilometers, passenger kilometers are shifted from the traditional mobility modes to micromobility. And then we have a LCA component that essentially calculates the differences in life cycle emissions per passenger kilometers between the original travel modes and the micromobility modes. So we have those two inputs that go into a scenario analysis, and that allows us to calculate the total mitigation potential. So the way we're doing this is essentially very simple. So we're calculating the total number of passenger kilometers that are shifted from the traditional modes to each kind of micromobility modes, and then we multiply that by the difference in emissions per passenger based on different scenario specifications. And the target regions that we're considering in this analysis were selected based on variabilities in built environment and transportation model share, economic conditions, and emission intensity of different modes and the energy grid. But also it's also a function of data availability, because the data that we want to use in most cases is not available. As a result, we're using 7 case geographies, namely the European Union, 27 countries, United States and Canada in North America, Australia, New Zealand, and Oceania, China and Japan in Asia, and Brazil and Peru in Latin America. Now, looking at the behavioral component, one of the key aspects that we need to measure is what is the modal shift, right? So from which modes we switch to micromobility. And when you look at the literature, the main approach is being this counterfactual method that asks respondents to recall their most recent micromobility trip and then think of the alternative mode they would have used if that micromobility was not available. So the way there is a study by Fernley and Weinstein that actually summarized all the reported studies in terms of trip modal shift. And you can see the report here by region between North America, Oceania, and Europe. And also induced demand, we suggest that the trip would not have happened if micromobility was not available. The problem with this literature is that it focuses on trips, and we're interested in distances shift. So when you look at the actual change in terms of distance, the literature is much more limited. So we found these 3 studies in the US, in Paris and Zurich, that allows us to calculate these correction coefficients to convert trip substitution to distance substitution. And the reason this is important is because if we assume that trips and distance are equal, or a one-to-one conversion here, then we're going to be resulting in bias, because some trips are going to be overestimated, and some modes are going to be overestimated and some modes are going to be underestimated. For example, if you look at the data from these 3 regions, walk trips tend to be overrepresented. You only focus on distance because walking trips tend to be shorter. Whereas bike trips, transit trips, and private car trips tend to be underrepresented because they tend to be longer trips. So to correct for that, what we did is we used all that data, and then this is a very simple algorithm where we actually use as input the trip-based substitution that is widely reported in the literature, and then we convert it to distance-based substitution based on these conversion coefficients that we can estimate from the literature. So the result is here. So you can see this is the estimated distance-based shift rates to micromobility in percentage. And what you can see here first is that there's a wide variability in terms of how many active mode trips are being substituted, with Oceania, Brazil, Peru, and North America having highest rates. But then you also see very large differences in terms of private vehicles, right? So especially ICE, so internal combustion engines, the substitution rates are much higher for North America, Oceania, and then to some extent Latin America. But then on the other hand, when you look at the rail substitution, the values are higher for the EU with 42%, and for Japan and China, which are also relatively railway-oriented regions. Now, moving on to the LCA components, I'm going to explain very briefly because it's not my main expertise, but we are accounting for, of course, the fuel cycle, which means the extraction of the raw materials, the production of the electricity and the generation, and also the distribution in the grid, right? We're also accounting for what's called tank to wheel, that is the vehicle operations, which means tailpipe combustion and the electricity consumption. And then we also account for vehicle life cycle that accounts for the acquisition of materials, the component manufacturing, including the batteries, shipping, deployment, maintenance, and service. So the fleet rebalancing that you all have been discussing so far will be included in the vehicle cycle, as well as collection and dismantling. So we use this both cycles, and then we calculate a functional unit that is essentially grams of CO2 per passenger kilometers for both reference years. And then to summarize these results, what you can see here are both the 2025 and 2050 LCA components. And I think the main thing to highlight here is that for micromobilities, most of the emissions come from the production, the maintenance, and the end of life, well as for the other vehicles, namely cars and rail and bus, tank to wheel and well to tank account for larger shares of the emissions. So these are the very important implications of the results that I'm going to be showing now. So in terms of our scenario designs, our scenarios are defined as a function of different market shares of micromobility and also the share of substitutable trips that shift to micromobility. We are using as a target population, the population between 15 and 65 years old. And the reason is that in many cases, these shared micromobilities are not available for kids or children. And also because of the fact that we believe that elder populations are less likely to change their behavioral patterns. We assume that the trips to be assumed to be replaceable are all the trips under 5 kilometers, and that the average trip rates and the trip distances are assumed to be stable between 2025 and 2050. When you look at the micromobility market shares that we use, we're using extreme market share, so 100% market shares for private mechanical bicycles, private e-bicycles, shared docked e-bicycles, shared free-floating e-bicycles, and then private and shared free-floating scooters. And the reason we're doing this 100% is because there is absolutely no way we can know what will be the future market share for these micromobilities. And also it allows us to observe more clearly the effects that the technologies and the operating or ownership systems actually have on emissions. And in terms of degrees of modal shift, there's a lot of literature regarding how many percentage of trips under 5 kilometers are actually substitutable to other modes, to walking or active trips. So but there's not in terms of the specifics that we want to focus on here. So we're assuming a load shift that means 10% of all the trips under 5 kilometers, and a high shift scenario where it's 30% of all the trips under 5 kilometers. Now, in terms of the results, what we're seeing here is the total passenger kilometers that shifted from micromobility to micromobility modes from other modes for the high shift and 2025 and 2050. So the first thing you have to see here is that irrespective, of course, you can see different variations across countries, but majority of trips that are being substituted are walking trips, distances, walking distances, railway distances, and bus distances, especially when you look at the shift in 2050. And then we look at the substitution patterns for cars, so namely for private cars or taxi or ride hailing. What you see here, the difference that you see between 2025 and 2050 is a result of the evolution of EV, the penetration, the increased penetration of electrical vehicles in the market, in the fleets, which reduces the share of ICE vehicles. Now, looking at the results directly, you can see here that this is the total net greenhouse gas effects on the different market shares. The first one that is in the top is the bicycle P, so that is private bicycle 100%. This is a mechanical bicycle, not electric bicycles, and you can see they have the biggest gains in terms of mitigation. But it's also important to note here that the worst performers are actually the shared free-floating systems. So whether it's e-bicycle or whether it's e-scooters, they actually result in net increase in emissions in total. And this is the fact because of the shared free-floating systems are the worst performance in terms of environmental, in terms of LCA, but also because, as I mentioned earlier, the modes that are being substituted. When you look at the mode level decomposition, this is a little bit of a complex plot, but what you're seeing here is every values that are on the above 0 means that are resulting in net increase in emissions. All the values that are below 0 means a net decrease in emissions, and then the black diamonds are the total, right? So across plus and minus. So the first thing you can see here is there's a big difference between zones. So in the case of Europe, where a large share of the substitution comes from rail, you can see that with the exception of the full private mechanical bicycle scenarios, all the scenarios are actually net positive, so they result in emissions, which is the opposite case for the North American case, so United States and Canada, where with the exception of e-scooter shared free floating in 2050, all the scenarios actually result in net reductions in emissions. The case of China and Japan that are more kind of rail oriented as well, you can see there's a mix, but the clear pattern that you observe here is that the free floating systems are resulting in in positive emissions across the board. Now, when you look at these results in terms of the total passenger road transportation emissions, what we see here is that the potential that we have in the best case scenario, so these results you're seeing here is the mitigation potential of micromobility in the high shift to private mechanical bicycles, so there is no sharing and it's all mechanical bicycles. The results are actually very moderate. So you can see a 0.6% mitigation potential for the EU, a 1.2% mitigation potential for North America, and in rather optimistic cases in Brazil and Peru between 3.6 and 4.7%. So to summarize, what these results show is that micromobility does not inherently reduce emissions. And even the best case scenarios, that is a high shift to private mechanical bicycles, mitigation is under 5% of current road transport emissions. So the net effect actually depends on the technology that we're using, but relatively to the technology that it displays, not the technology alone. And a big part of all this is the fact that the micromobility's footprint is dominated by manufacturing, which accounts for 50% of the LCA emissions, and then the collection and charging logistics, right? So that accounts for 43% of the LCA emissions. Then in terms of urban formal structure, there's a lot of literature in the transportation planning field that shows that the built environment shapes travel behavior. So what we observe in our results is that micromobility actually yields the highest benefits in car-oriented urban structures. That means lower density, lower land use mixes, and lower transit access, because it tends to replace car, taxi, and ride-hailing for short trips. Whereas in the compact case of rail-oriented cities, micromobility actually risks cannibalizing the greener modes instead. Of course, a big caveat of our study is that we did not capture, because of some limitations in terms of data and resolution, the micromobility transit synergy. That means that micromobility can actually increase the first mile, last mile access, and this is not captured in our study. So in terms of the limitations, there are a lot. Modal shift rates and emission factors are very uneven across geographies. So most of the data comes from European, North American, and Japanese sources. So there is greater uncertainty for Latin American and Chinese estimates. The emission factors, also there's a lot of variability due to methodology and context-specific assumptions. And then the modal shift share information is actually self-reported and counterfactual, so it's subject to hypothetical bias. And there is not a lot of data on the conversion between trips and distances. So finally, as I just mentioned, there is no model. We didn't consider the micromobility transit synergy effects, which will require final spatial resolution that our data allows. Thank you very much. That is all for my presentation. I would like to go to the Q&A session. Okay, so I assume average trip rates and trip distances constant. How sensitive are the results of this assumption, considering that travel behavior could change substantially? Yes, that is a very interesting question. We have not tested these results yet, but one possibility is in the case of developed countries like Japan, or even Asian societies like China as well, or in the US or EU, I think that the travel behavior patterns are in terms of trip rates have stayed relatively stable. So we can talk about what is called peak travel But yes, it is possible that the patterns change, but we don't really not necessarily know in what direction. I believe that our results will probably be more sensitive for the upcoming economies like Brazil and Peru, where we might still observe some increases in let's say trip rates with economic growth. But I think for developed economies, probably not the case. But yes, this is something we want to consider. And what would be the factors pushing for travelers to shift from public transport to micromobility? Well, we do not know, right? So we ask because the way the data ask is they ask you to think about your last trip. What will be the mode that you would have used instead? So we do not really know why is this happening. But I think in many cases it's convenient, right? Because if the trip might require, for example, awkward transfers or something like that, then people might prefer to just switch micromobility that might be faster. So one hypothesis that I have, and I don't have quantitative evidence to back this up, is that you saw that the highest substitution was for Europe. And I think because the tram penetration rate in Europe is much higher, so you usually use tram for much shorter trips, and they're easy to hop in and hop out. So I think those trips are also kind of easy to substitute with micromobility in many cases. But the actual mechanism behind the shift from transit to micromobility, I do not know. Are there any other questions? Okay, so if there are no questions, because we still have like 20 minutes, I would like to open the floor for questions to any other of the presenters. You can unmic yourself directly if you want, or you can just post them on chat.
Sorry, may I ask a question using
Yes, please.
directly? So, I remember one of your conclusion is that for micromobility, sorry, let me turn on the video as well. So, like in terms of life cycle analysis, so
Yes.
the emission actually come from the manufacturing process.
Yes.
So, because I think around 10 or 8 years ago, there was once like news about in mainland China the massive amount of shared bikes being disposed and then piled
Yes.
up as trash. So do you
Yes.
think we should like set a rate of the expansion of the micromobilities to avoid it happening in the future? Like, do not overproduce the
Yeah.
micromobilities.
That is a very good question. Actually, something that I needed to point out here, one of the reasons that shared micromobilities actually have such a high emissions is because the lifespan is very short. So, and this have seen particularly to be the case for shared free-floating systems. But even when you look at the other, like for the shared dog bicycles, apparently, according to the literature, does not seem to be the case. So yeah, we have a problem there. The lifespan is very short, so they're not used very efficiently. So you end up in a case where you have a vehicle that is used 1 or 3 times per day, and then it doesn't last even 1 year in many cases. So that might have severe contributions to worsening the performance of the LCA. So one possibility will be, as you just mentioned, I don't know if we can control the production, but if we can find ways to make it easier to, or not easier, if we can find ways to make the lifespan of these micromobility vehicles longer, that would increase considerably the LCA performance of these models, of this mode, sorry.
Okay, thank you.
And that's what this is. Sorry, Fasal. So aspects of FFS that free floating are considered more sustainable and environmental friendly. Sorry, I don't understand the question. I think it's the opposite, right? Free floating sharing systems are actually less perform worse environment in terms of environmental because of I mentioned like the lifespan of the vehicle is just shorter. Okay, great. So actually, we would like to ask the team that is working on the optimization. Is this the life cycle thing? Have you observed this in the Chinese market that some vehicles, like the dog vehicles, having a better like lifetime, lasting longer or having less problems than the free floating services?
Sorry.
I guess I was wondering if you have any information about this, like in terms of like the duration of the vehicles, right? I think in one of the presentations, the repair was considered, but have you ever considered the repairing the bicycle, right? But have you ever considered like this kind of the life of the vehicle itself? Like how long do you think that these vehicles last? It's like 1 to 2 years or?
Runqiu, do you have an estimation? I'm not sure.
Based on your experience, because I know in your case your optimization is too short span for focus on that, but I'll be interested to know if you have any information about that.
Can you hear me? Okay. So
Yes.
So there are some research on so there's a two concept. One is called collection of broken bikes, and another one is called recycle. So basically, recycle means like you send them back to depot, and sometimes you also have a repair. I think currently the problems in Chinese, like I just talk about the observation in China here is like.
Yeah.
They're keeping upgrading the bikes. So like so like they're now installing like the racks for the cell phones, because some like bike riders, they want to use the shared bicycles to like do some exercise, and
Okay.
they're adding the Bluetooth. So the Bluetooth to like they do not require the physical locks here. So now the duration, maybe the usage of so previously I think some damaged bicycles it is not cost effective to repair it. You may just have to
Okay.
broken. So like for 1 to 2 years is on average, that's I think on average, because they are upgrading the series of bikes very often. But this brings another problem, like some old versions of bikes, they cannot be easily upgraded, and they may just left on the road.
So you end up in the situation that even because you're trying to upgrade the quality of the service, then the solution is just to throw away the old bicycles.
Yeah.
Is that what you're saying? Okay.
Yeah, and you can see, and this is not just throwaway, it's just because of the upgrade. Like for some cities, there are not so much demand, so there will be piles of bikes just just parked at some like garbage areas. Yeah, so this is like over invest and over deployment of the shared bicycles. Yeah, this is other problems.
So, but going back to your own research, wouldn't that affect the profitability of the operators, or are these public services or publicly subsidized services, or because I mean, if you're running a business, you would like to minimize the waste, right? You're trying to make use of these bicycles in one way or another, but it seems like it's just easier to throw them away.
Yeah, I think so. I don't know to be honest, I don't know how they handle this, but I don't feel like, especially in China, they like to make use of the component of the bikes. Like they just throw them away. Yeah, I think.
Okay. Are the bike sharing providers are private or they're public?
private. For those shared bicycles, currently
Okay.
they're all private companies. For like docked stations,
Yeah.
most of them are run by the government. So it's like the public.
Okay.
Yes.
And do you think they're profitable?
I think so, but I'm observing the huge increase of the price
Okay.
on the service. So I believe it's coming to a stage where
Okay.
they cannot just use those cheap price to affect the users. Yes.
Okay, so you think it's kind of like a similar model to what like ride-hailing Uber used to do, right? They actually had the
Yes.
kind of subsidize the prices to capture the market, and once you have all the users, then you just eliminate those subsidies and go to the real cost structure. Do you think that's the
Yeah.
strategy? Okay. Interesting. Yeah. So I mean, when you look at those kind of discussions, then that's the reason that in many cases, even though these micromobility systems tend to be sold as environmentally friendly, they end up not being so because the vehicles don't last long enough.
I think they're achieving a balance. Like like years ago, there's a saying that the over deployment of the shared bicycles that makes this thing not that attractive for the users. And some users would say, I would rather take other ways. Like I would take some just increase my walking distance willingness rather than paying for like $1 or $2 to ride just like in 30 minutes. But now they are achieving a balance. They're testing the boundaries of the acceptance of the users, and they're
Okay.
trying to achieve this balance. Now I find more people still tend to use it. Yeah, they are accepting this. But the regulations and the parking restrictions and how they are impose these regulations, this is still a huge problem. As you say, we can see some bikes parked at very unreasonable areas. You will see some bikes just lying there.
Yeah, I noticed in Europe that, and I mentioned this earlier to Reza, that they're trying to clamp down on the free floating services, right? So they even if they don't have a station, they're trying to have like geofencing, so you cannot put them back anywhere because the problem is like if you can park anywhere, then you have a problem. You cannot guarantee the space for pedestrians or for bicycles, etc., etc. So yeah, I think the market might be trying to find its way.
Sometimes in the rush, I just encountered like if I ride to some areas which is not suitable to park a bike, and I want to just park it here because I'm in a rush for something else. And the app in China, they would pop up a repositioning fee to the users, like $2 to $3. If you must park there, you pay this and you just leave.
Interesting.
Yeah.
So China is applying a market mechanism. So it's like, okay, fine, you can leave it there, but you're gonna pay a lot of money.
Yes.
Okay, I didn't know that.
They still don't want to lose this user, I think. So they're just trying to test these boundaries.
Yeah, that is interesting. So we have still like 10 minutes. So I think now is just a free discussion. Anything you want to talk about related to micromobility is okay. So maybe for the other presenters, Reza as well. If you have anything you would like to add.
I think in the chat box there's a follow-up question about.
Oh, sorry. Might be the same. What are the main factors for travelers to transfer from public transit to micromobility? Yes. So in our case, Tiffany, we use it's the same distance for all the modes. So we don't know why they will transfer from micromobility and not other modes. But I'm guessing the main reason is that it's not necessarily what explains it, but we observe higher shares where the transit use was already high. So in Europe, for example, we have a very high use of transit. Then you end up having a higher share of switch from transit as opposed to cars. And one of the other reasons might be the fact that you just have most of these services are located in city central areas. So they're probably at least in Europe or in Japan or in China, there is less possibility to switch from car because people are not driving anyways in the city center. So that is my explanation. But regarding why from transit and why not other modes. I'm not sure I know the behavioral mechanism, but we know that the original model split is a very good predictor of that. Reza, sorry, you turn your video on. Was there something you wanted to say?
No, thank you so much for the information you gave us. It is so interesting.
Can you talk a little bit then, like in the remaining minutes, about how is micromobility, the micromobility market in Australia, right? Like,
The only thing I can say here, in Brisbane, there is just one system. It is just free floating system.
okay.
Yes, so rebalancing here is a big, challenge, definitely for companies. So it is definitely it is not efficient. It is so in this way they increase the cost. They pay based on the distance they utilize, based on the time they utilize. So it reduces definitely the customers as well. So I'm trying to find a way to minimize this inefficient cost. I mean, user-based rebalancing as well. It is definitely costly, but I think I'm probably finished that by proposing a model, and we just utilize another the crowd shippers instead of trucks or user-based rebalancing, or so in order to reduce the cost, rebalancing cost and battery swapping cost. At the end of the day, hybrid system definitely completely eliminate the battery swapping cost. Because by considering two strategies, for example, one strategy is they can say, okay, that truck can pick micromobility devices with low state of the charge from free floating zone and drop them in stations. So in this way, they can be charged. And based on this strategy, they can eliminate the battery swapping cost, which is significant.
Okay.
And another is, I think, to me, a significant cost is related to rebalancing and battery swapping. So as you mentioned, geofence. So here, there are a lot of users just utilize that, but at the end of the day, they throw away, micromobility devices. So in proper, parking. So it is a big challenge here, honestly.
Do you think that that pricing system that sorry, Runqiu?
Yeah.
I'm killing your name, sorry, in the pronunciation, but
It's okay.
do you think that pricing system works? Because it seems to me like very intuitive. You charge a very high price for parking outside the ideal zones, then you can probably compensate some of that rebalancing costs. Is that applied in Australia as well?
Not in Australia, but it is interesting way to develop this. Honestly, it is very interesting because when you have a dynamic price for different area, you can rebalance the system based on increasing or decreasing the price. It would be interesting, I think.
That's think cool. You mentioned you're in Brisbane, so like I just watched a vlog on YouTube. Like a YouTuber just traveled to Brisbane, the Gold Coast, and they're saying that this is a chill place, and even the shared bicycles are chill. They're just lying on the grassland everywhere. So I think it's challenging. Like just near the beach, you can see the shared bicycles riding onto the grassland. This is, I think it's challenging. Hey, sorry.
Yes. It is common here.
There's no penalty for the users to do this.
I don't think so. But when you unlock the micromobility devices, you should lock that. So, and after they lock, micromobility, they can, through, a river, there are a lot of micromobility days away in the river.
It's a problem. Okay, guys. So I really like this discussion. I think maybe we should have some more of this, like just free discussion, because I think it's more it's fun. I have to go to the next session in another room, and I guess the host of this next session is probably Professor Szeto, maybe. So he can take over. But it was great, and I hope we can stay in touch. Maybe we'll meet in person in some conference. I know Australia has a lot of conferences next year, right?
Yeah, ATRF, I think so. Yeah.
Yeah, IATBR also, right? So yeah, good. Anyways, great presentation, guys, and I'll see you around.
Thank you. See you.
Okay,
Okay.
thank you. Thank
Bye-bye.
you. Bye-bye.
Bye.
Testing. Testing. Testing, can you hear me? Okay. So I suppose it's the time to start the new section. So Would I invite the first presenter to share the PowerPoint? So, so is the first presenter here? So do you know your presentation sequence following the schedule online?
Me, Dr. Lubna.
So
Lubna
are you the first presenter?
Yes.
Yeah,
About
so
top generation.
yes. Could you share your screen? Now I think it's the time to start the presentation.
Okay. Do you see my
Yes.
presentation, sir?
Yes.
Okay.
I can see. So you can be larger. So you have roughly 15 minutes to present, leaving 5 minutes for Q&A. So you may start.
Yes, okay. Thank you, Doctor. My name is Lubna Amire from University of Science, Malaysia. I'm from Jordan. Today I will present a review paper titled Review of Generation and Traffic Impact Assessments using Machine Learning for Effective Land Use Planning. This work was conducted and collaborated with my supervisors and co-authors, Dr. Noor Sabahiya and Dr. Ahmed Farhan. The most important here, why is improving traffic generation is very important for several reasons. That the traffic impact assessments is crucial in urban and transportation planning, and also traffic generation is the most significant component in traffic impact assessments. So it influences on land use decisions and sustainable transportation strategies. On the other hand, the traditional forecasting methods have limitations and represent complex urban conditions and local travel characteristics, especially in developing countries. Also, machine learning offers a promising approach to improve trip generation forecasting accuracy. The research motivation here that we determine the existing challenges, such as the research focus on the need of identify gaps in trip generation forecastings. Also, the traditional trip generation failed to represent local urban conditions accurately. Although also machine learning techniques have improved forecasting by considering land use, demographic characteristics, travel behavior, socioeconomic conditions, but the applicability and transferability of these models across different urban settings remain limited. So the research question here, how can machine learning improve trip generation forecasting, and what added value do these improvements provide to traffic impact assessment practices? So the methodology of this systematic literature review conducted to explore the relationship between trip generation, machine learning, and their influence on traffic impact assessments. The protocol we use reporting standards for systematic evidence synthesis ROSES protocol. And the research questions was formulated using PICO framework. The population was trip generation, interest, machine learning, context, traffic impact assessment. The search strategy, we use a primary databases such as Scopus, Web of Science, and secondary databases such as Science Direct, Springer, Taylor, and Francis Google Scholar. The keywords we use trip generation, traffic impact assessments, machine learning, artificial neural networks, artificial intelligence, and the search techniques we use Boolean operators, phrase search, and wildcards. This is the diagram of ROSES we use. The total records were 2,834. So we excluded 2,518 due to that cite the range of our period of studies, which is 2019 till 2026. And these records, some records is not English, and some others it's not journal articles. So the records become 349. We exclude the duplication, and the total become 299. Then we exclude because of title screening, abstract screening, and content screening. So the total become 29. This is the characteristics of the reviewed studies of the period between 2019 till 2026. This is the publication year distribution. We have here 29 studies from 15 countries. In this period of studies, 2019 till 2026, the publication become to increase in 2020 with 4 articles, then the peak at 2021, 8 articles, then decrease and increase again in 2025 and 2026 because of its importance of using machine learning in trip generation, and focuses on that. Here we have most studies from USA, 6 studies, followed by Malaysia, 4 studies, then Thailand, 3 studies, China, 3 studies, and other several countries. Here is the geographical distribution of this studies, and this indicates the important multidisciplinary of interest in machine learning based trip generation. We have here a research design of selected articles. We have quantitative articles with 54%, followed by mixed articles, 29%, and qualitative articles, 17%. This indicates that the research in this field is primarily a quantitative model development and evaluation. We here have a journal distribution and quality. Most reviewed studies published in a wide range of transportation and planning journals, such as we have International Journal of Management Science and Engineering Management with 3 studies, and Transportation Research Part A, Policy and Practice, 3 studies, and the remain studies distribution in reputable journals, which demonstrated also the multidisciplinary nature of research on machine learning for trip generation. We have here also Scopus quartiles of these published journals. In Scopus, we have 66% Q1 and 34% Q2, while WOS quartiles published journals Q1 48%, followed by Q2 28%, and 21% Q3, finally 3% Q4. This indicates that the reviewed literature is supported by high-quality scientific publications. The main research themes in this period concentrate that we have trip generation forecasting challenges, about 29 studies. It deal with many issues such as the lack of contextual variables, overestimation, uncertainty, the absence of local trip generation models, data scarcity, and transferability problems, followed by urban planning decisions with 15 studies and prediction model developments with 15 studies. These 2 themes, as we see here, that it's most important in planning stage, and how the models it's very important in this planning stage. Followed by the least is the innovative tool of machine learning with 7 studies, and urban sustainability 7 studies. And this is the least that indicate its opportunity for future research of these 2 themes. It's very important. We have a comparison of prediction methods reported in the original reviewed studies, because these original reviewed studies have an evidence of the prediction methods, data sets, validation methods, transferability, and we exclude the review paper to avoid the double accounting evidence. So most studies have used models such as multiple linear regression, log regression, artificial neural network, support vector machine, random forest, geographically weighted random forest, and Institute of Transportation Engineering trip generation methods. We brief the findings of this table as that machine learning techniques outperform conventional by prediction nonlinear trip generation, but on the same side that the regression must wide use because of its simplicity and interpretability. Also, most of the prediction models rely on land use, socioeconomic, and gross floor area as a variables as a key trip generation predictors in reviewed studies. Also, prediction models were commonly validated using statistical evaluation and comparisons with conventional methods demonstrating increasing emphasis on model reliability. Most studies developed context-specific models using local data sets, highlighting the influence of local urban characteristics on prediction accuracy. Here we will return to the answer of the research question that how can machine learning improve trip generation and what added value to provide traffic impact assessments in practices. So the machine learning improved trip generation by capturing the nonlinear relationship among their variables of trip generation, achieving a higher predictive accuracy than conventional regression models. And this will reflect as improvement in traffic impact assessment to better reflect local urban conditions, support more reliable traffic forecasts, and facilitate more cost-effective infrastructure planning and mitigation decisions. And this is most studies talk about cost-effective in traffic impact assessments. The research gaps from the reviewed studies we had limited evaluation of model transferability across different cities and regions, insufficient external validation using independent data sets, few studies compared multiple prediction methods using the same data sets and evaluation criteria, limited emphasis on model interpretability alongside predictive accuracy. So the future research will be developed transferable prediction models that can be applied across different geographical contexts, validate models using multi-city and independent data sets to improve robustness and generalizability, develop interpretable and hybrid machine learning approaches that balance predictive accuracy and interpretability. Here, that most prediction models give us outcome, and these outcomes will use by urban and transportation planning, and they want to understand these outcomes and interpretable of these outcomes to reflect it as a practice in use. So as the accuracy in machine learning is very important, also the interpretability of these outcomes is more important. Also, we have a conduct comprehensive comparisons of multiple prediction methods using same data sets and evaluation criteria. Thank you for your listening, and if there are any questions.
Okay, thank you very much. May I invite the audience to ask questions? So I haven't seen any question from the blog, so I just wonder, so based on my understanding, the machine learning is actually depending on what data you input. So in all the study you view, so how large is the data set? So because if you don't have enough data set, basically the machine learning model may not perform very well. So my first question is, in the all paper you view, roughly how large is the data set for trip generation?
The large of data sets, most studies in developed countries, they have large data sets. Some of them depend on phones and cloud data. But in developing countries, this is the problem, that they didn't have sufficient data sets, and at the same time, they didn't have a manual of the traffic impact. Because of this, they didn't have sufficient data sets that they can use. Because they also didn't have a financial for that.
So
because of this,
did all the paper mention roughly how big is that data set? So I want to get the idea how big really 10,000 data set, 10 years, how big really? So compared with convolutional model, what is the difference in terms of the size of the data set?
the term of the size, yeah,
My understanding is that for convolutional
2000,
model,
2000, some of them is 2000s and
so
more.
okay, but for conventional, I don't think you need 2,000, right? For conventional model, but machine learning model.
Yes,
So you
yes,
said
yes,
machine learning
yes.
2,000.
Conventional, no.
Okay.
Yes.
So much less, right?
Yes.
Okay. So because you
machine
use a
learning.
lot of data. Yeah.
Okay, sorry, Victor. Sorry.
Yeah.
No, I'm finished.
Okay. So for machine learning model, you roughly say using 2,000 or more data set. So my concern is that if you use a lot of data, normally it will fit the data set very well. But if you want to propose to have a model that is transferable to other locations, so basically when you develop model, you need to have data set include many different countries. So if that is the case, you have an average model, but the predictability may not be very good because normally, as far as I know, this type of model fit very well to a data set. But if you want to have a model that can fit all over the world, you need a lot of data set from different parts of the world, and that will become a average model only. So I just wonder whether it is feasible or not, but I'll let you to think about it later because I just concerned about this transferability point, which is good to be transferable, but as far as I know, most of this type of model fitting is not good for other applications. It's only tailor-made for one specific issue. If you want to work on it on another situation, basically you need another model. Although it's still machine learning, but you need to fit another model. You have a different set of parameters or different factors. So you probably need to rethink about how to make it more general. Data set issue and also overfitting issue. Because you normally it's better because you have more parameters.
Yes,
But if you want to consider many different cities, it's more difficult. Because one factor may be actually just for one country or one city, but this factor may not be important for another city. So that's why the model is not transferable. So I still cannot see other questions from the chat box. So I also didn't see any hands raised up from the audience screen. So if there's no further questions, I would like to thank you to have a very good comprehensive review presentation. Thank you very much.
Thank you, Doctor.
Thank you.
Thank you.
Second presenter is the second presenter here from Japan, I suppose. About dynamic.
Yes, sir. I'm here, sir.
Okay, so could you share your screen?
Yes. Yeah, I think you can see my screen.
Not yet. Yeah, now yes. Okay, I can see it now. I can see it now. You can make a full screen.
Yes, sir. Thank you very much for this opportunity. So my name is Dongono Isola Edward from Hiroshima University, and today I'm going to present about person re-identification, more specifically, dynamic optimal transport with view-guided prototype propagation for structured person re-identification. So let's talk about the problem and the motivation. So what is person re-identification? Person re-identification is the task of identifying a person between two different cameras. And this problem has application in transportation, especially in the pedestrian flow estimation. So a query image ranks a gallery of candidates frames by descriptor similarity. But viewpoint.
Sorry for interrupt. I think you may have dual screen. I cannot see the slide flipping over. I only see your first page. I can only see your first page. I cannot see second and third page. I cannot see also using full screen. So maybe you have a dual screen. So I think you need to swap. Yeah. Oh, yeah, I can see page 3 now, but you didn't use a full screen mode. The other way around. The other way around. The other way around. Yeah.
Can you see the page?
Yeah, I can see page 3 now, but I also see next line. So basically, the other way around. Basically, it should be the other way around. Yes, but you didn't click on the full screen mode. You didn't click on the full screen mode. Not this one. Yeah, this one. This one. You click this one.
Oh, but when I click in this one, I have two screens.
Maybe your file size is too large. So if you have problem for this one, maybe you don't click the full screen mode, but you make the main size larger. Or you need to manually make sure that you are changing. Now it's better. Yeah. So now you're on page 3. Yeah. Make sure that you can click the button one by one, so that I know you are talking about a different page.
Yeah, sorry.
It's okay.
Okay. So I was saying person re-identification has some problems. For example, if you want to re-identify someone from one camera in another camera, we have viewpoint elimination, pose, and occlusions that will diminish the algorithm ability to re-identify the person. Actually, the standard encoding is using a full image. So each image is compressed into global vector. For instance, using global average pooling, as you can see in this image. But this averaging washes out small identity. For example, if someone has a bag on one shoulder, or if the part of the body is occluded. So local evidence survives only in regions that are partitions, weighted, and matched with care. So part-based descriptor preserve local evidence, but their benefit depends entirely on how regions are partitioned, weighted, contextualized, and matched. So here in this image, you can see that we have two different types of partitioning. In order to keep local evidences, we have horizontal or top-bottom partitioning, and we have vertical or left-right partitioning. So in this study, we use the vertical partitioning. So what are the conventional assumptions of the common pipelines? So they use predefined feature map partitions, and there's limited or no interactions between the parts of the images. And also they don't have adaptive fusion, where local regions receive equal or predefined contributions. But those assumptions have some weakness. So one stripe, one partition may be dominated by background or occlusion, and some accessory may cause invalid matching of this section. For example, if a part has a bag and you want to match another part in another image without a bag, that is going to make accuracy degradations. And also pose and viewpoint variation can break fixed stripe correspondence. That's why we believe that a rigid stripe to stripe comparison cannot redistribute the correspondence when the same local cue is displaced. So that is why we propose what we call set-to-set matching. So in this image, in the first image, you can see the fixed one-to-one matching, and in the other part, in the set-to-set matching, we are matching a group of elements with another group of elements. And in this way, one element can correspond to different elements that have close similarities. So which method are we using for this set-to-set matching? Actually, we are using the optimal transportation. with sync-on regularization. So optimal transportation finds the least cost soft assignments between two stripes, and entropic regularization keeps the plan smooth and differentiable, matching between the stripes. So the correspondence becomes soft, flexible, and if the evidence move, for example, if the back move from one stripe to another between two different images, that is not a big problem. So our research questions, so how should local regions be compared when query and gallery evidence is neither equally reliable nor spatially aligned? So to reply to these questions, we are going to use reliability-derived optimal transportation marginals, inter-stripe contextualizations, and view guide prototype propagations. So we are going to explain those concepts in the next slide. So what is our methods? So this is our framework. First, we have an image that we feed inside a deep neural network backbone, and this image is partitioned and masked. Then we use refinements in two levels. So the first refinement is graph neural network within stripe and transformers equal stripes. Then we modulate our vertical stripes with the orientation using orientation prototypes. And finally, we use optimal transportation to match two images from two different cameras. So why verticals? As we just explained, we want to keep the matching correspondence, even though a local queue is displaced from one image to another. But however, in this study, we are not assuming that vertical partitioning is better than horizontal partitioning. So we are going to talk now about our soft mask foreground. So we want to isolate or to differentiate the person from the background. And for this reason, we are going to use the activation energy in the image. We are going to explain now. So we have a person, and we use the activation energy of the image to isolate the person from the background. And this activation energy is passed through a soft mask grid. So we obtain, for each vertical stripe, we obtain some reliability weight. So if beta, so those numbers are called beta, they are the reliability weight. So if beta is high, it means that the stripe is dominated by the foreground, by the person. So it will be transporting more mass during the optimal transportation matching. But if beta is low, it means that the stripe is dominated by a background or occlusion. So how are we building the descriptors of our stripe? So we divide our image into many cells. First, we compute the confidence, foreground confidence of each cell. Then we use a weighted pooling plus L2 normalizations. And then we have the aggregations of the normalization of each cells. So for each cells, we normalize, we sum and we divide by the sum of the foreground reliability from cells, and then we have the descriptor of our stripe. So one stripe has its reliability scores, which is beta, and those scores are obtained, those numbers in this image. The refinements, we use graph neural network for vertical message passing in order to keep top-bottom correspondence inside the same stripe. And then we use transformers for self-attentions between stripes. We use transformers because they are good in the long-range correspondence. So in using this method, we can obtain our weight for optimal transportation. The weight are the dynamic marginals. So the dynamic marginals allow us to transport mass with respect to the importance of the stripe. In an image, as you can see here, after foreground derived mass, we can see that the outside stripes transport less mass. And that is because in an image, a person is usually in the middle of the image. So after that, we use orientation prototypes to adjust our cost matrix. So we have 5 body orientation: front, 3/4 front profile, 3/4 back and back. So we have view estimation, and then we use we propagate our view context using a transition matrix. So a prototypes encode body orientation, not camera or identity, and then we use a gate correction. So dynamic similarity modulation before optimal transportation do not modify the stripe. They are just modulated. In order to build our prototypes, we use manually averaging over 600 annotated frames, and this method is just experimental. Actually, the coverage is calibrated. The coverage and calibration are limited. So this is our experiments. We use a mass dataset. Mass means motion analysis and re-identification sets. So it uses 6 cameras and more than 1,000 identities. So 7 camera match are removed, and our metrics are the mean average precision and rank 1, 5, and 10 accuracy. And in order to do ablation study and to isolate the contribution of each part of our framework, we have 4 experiments. In the first experiment, we use uniform optimal transportation. It means that the weights are uniform. And then we use dynamic OT. In dynamic OT, we use the reliability derived marginals. In experiment 3, we add the contribution of the transformer. And in the last experiment, we add the contribution of the view guide prototypes. This is our results. We see that when we move from experiment 1 to experiment 4, we have an increase of the mean average precision, as well as an increase of rank 1, 5, or 10 accuracy. But we didn't succeed in beating the baseline, which is using the global image. But actually, the rank 10 accuracy was better than that of the global baseline, even though this improvement is weak. So from this result, we can say that our method makes a reordering of the images. So reliability weighting reorders the entire ranked list, and it is consistent with marginals down weighting background heavy stripe across all relevant match. So there is a weakness in this result. So the shortfall against the global branch concentrates in maps, not in deep rank. So the stripe model usually retrieves a correct identity, and ordering consistency is what remains. That is why the global baseline still beats our method. So as a result, we can say that the stripe branch is complementary, not a replacement. And we have a fusion hypothesis for the next experiment. We believe that global score provides stable cost retrieval, while stripe optimal transportation acts as a ranking corrective for occlusion, misalignment, and unilateral associations. What is for the last slide is about the future works. So we want to experiment global stripe fusion. So global score gives stable cost retrieval, while stripe optimal transportation is tested as a ranking or corrective signal for difficult occlusions. The second one is protocol alignment. We want to evaluate our framework as the standard mass tracklet level. So now we are working in image level. A tracklet is a kind of trajectory that is built for with the frames during the movement of a person. Usually, mass tracklet level or tracklet level have a mean average precision that is better than that of the image level. And now we have to replace our manual prototype derivation with a learned orientation representations. And finally, we need statistical hardening and cost control. Horizontal versus vertical ablation, sensitivity sweeps, and repeated seed evaluation. We also plan to reduce pairwise OT costs through global to local candidate filtering, caching, or top key restricted transport. So thank you for your kind attention.
Thank you very much. If you have question, please type it in the chat box. So I have a quick question, which is about the multi study. So when we need this matching, can you mention the application of this matching method first? Any real world application? I missed a few. Yeah, I probably missed some slides. What is the real application for this type of methodology?
Yes, so when a person is moving, or when a person is moving on the street, if an image, the camera is capturing a person seen from face, and then another camera is capturing a person seen from profile, for example, actually, some studies, some experiments we did show that the orientation, so the angle of being captured reduce the accuracy. So we want to solve this problem by matching based on not only from the whole image, but also based from the orientation.
So let me rephrase a bit. So for example, am I correct that a police want to check a person? So they need this type of info to help them matching the trajectory of the person. Is this a real application? Who you use this method? Is a police want to check a person, a suspect, for example, or is a transportation people want to calculate the average walking speed of a person? They need to match the people first. What are the real application for this type of method?
Is pedestrian flow estimation for origin destination mapping.
You want to estimate the origin destination of a person.
Yes, Professor. Like automatically.
Okay, so you want to know the OD of a pedestrian. Okay, this is your real application. Okay, I'm thinking about something else. Okay.
No, it's not about surveillance. It's about transportation planning.
Okay, so you don't care about the pathway. You only care about the origin and destination.
Yes, doctor. That is the
because
aim.
I'm also thinking about you may have more than 2 images. You want to check the trajectory of a person.
So we want to take maybe if we have a road, what is the value of person that is going to this direction during this period of the day? What is the amount of people going to another direction, provided that this volume of people came from this direction? That is the application, the objective.
Okay, this is more than origin destination. So because some study may interest where the pedestrian will go, there are multiple paths. There can be a good choice of a pedestrian because this affects the rent value of a shop. If more people walking on a street, the value for the rent is higher. So I'm thinking about more application about this. My second question is about the methodology. So you use GNN. So is this really common to use GNN for this application, or could you use other machine learning method to work on this?
The main backbone of the study is the convolutional neural network, OSNet. So the name of the convolutional neural network is OSNet. However, when we want to build the representation of the stripe, in order to keep the top-bottom structure of the body, we use graph neural network for vertical passing, because graph neural network is usually used to connect elements. So we want each cells to be aware of its neighbors. That's why we use graph neural network. So I believe there are other machine learning methods that are able to do that.
Yes. Why I ask this because I wonder, because your accuracy is roughly about 80%. I wonder whether if you use another method, not GNN, will the accuracy be improved? So I want to see a benchmark. I want to see a benchmark. So is GNN classic? If it's classic, could I use another one so that I can improve the accuracy? So I just think about from this direction. So that's why I asked you why GNN, not others. So you may think about this. The referee may also ask you about this. Why GNN? Do you have a benchmark compared with another machine learning model? So that you can improve the accuracy, or you can show that this accuracy is the best already. Okay. No, I'm not sure the accuracy 80% is good enough, but you probably need to just, although you said that it is a complement to existing method, because I don't know what is the acceptable percentage of existing method. 80% to me is not really high if you want to match the two images, but I don't know the acceptable percentage in the literature, so you better to check.
Thank you, Doctor.
Okay. Yes, I don't see other questions. So if not, thank you very much. Thank you for your presentation. Thank you. So may I invite the third speaker? Is the third speaker here? Should be from Bangladesh University of Engineering and Technology. About the multimodal travel behavior. Is the third speaker here?
Hello.
Yes.
Yeah, I'm the third speaker, Trina Shaha from Bangladesh.
Yes, thank you. Could you share your screen?
Yeah, sure. Can you see the screen?
Yes, I can.
Okay.
Yeah, you may start now.
Okay, thank you. So, greetings to all the session chairs and all present here. Today, I'll be presenting my work on multimodal travel behavior in Dhaka, evidence from a constrained urban transport system. My other co-authors are Famina Hassin Bibha and Dr. Annesha Enam. As our topic is about multimodality, so at first we need to know about why do we care about it. So mode choice gives a partial view that whether a mode is chosen or not. And we have seen a lot of studies regarding mode choice in transportation literatures. But multimodality reflects the travel flexibility also, like whether a mode is chosen and also how much time is used here, also from which point of view a person is choosing a mode, like out of choice or out of constraints. So multimodality reveals how individuals combine multiple modes throughout their day in their travel pattern. Now, in individual level multimodality, we can see here two scenarios. If we take the bigger aspect, we can just see that there is only 50% modal split, 50% uses car, 50% uses transit in scenario A. Also in scenario B, if we take the statistics only, we can also say that 50% car and 50% transit. But there is a big difference in between these two scenarios. Like if we see the first scenario, here the individual multimodality is very low and the modal behavior of the peoples are also very rigid. Like 50% uses car only, and also 50% uses transit only. So when a crisis hits or a policy changes suddenly, people takes time to adapt with that policy or with that change. But in case of high individual multimodality, the modal behaviors remain flexible. People are more accustomed with both the car and transit equally. So this is a high individual multimodality example. Now, Dhaka, the capital of Bangladesh, the study is different here because in the capital of a country where the low automobile ownership, like the car ownership is very less, it's almost 2.5 per 1,000 households. And also, there are a lot of informal modes like auto, CNG, Lagunas, and battery-driven rickshaws like this. So, the fragmented service is seen here. No policies are also there to unfragment the service. So in such case, in Dhaka, the study is very crucial. So the research gap we have found till now that most of the multimodality literatures are from Western countries like Europe and North America, where the formal transport system has been seen and also interpreted around car dependence. There, multimodality is used from perspective of environment issues. But actually, the missing link is in Dhaka, who is actually multimodal. We have tried to find it out in our study. And also, what does multimodality mean in Dhaka? Do people choose the modes out of choice or constraint or unequal access? What drives them towards multimodality? And also, mode participation merely doesn't capture modal dependence. Also, informal modes remains underrepresented. And individual multimodality is not measured. That's the insufficient part. The main objective of our study here, it quantifies multimodal travel behavior using some continuous indicators from diversity, concentration, inequality, and group-based perspectives. Some indicators have also been mentioned here, Gini, Thale, Atkinson, Delton, and Ompai. Also, demographic variation of multimodality have been seen, like who are, which type of people are, or how the indicators vary across different demographic groups. Socio-demographic variables have been considered here, and the method used was multiple linear regression modeling. The data we have used for our research or for this work is a very rich data set that has been provided to us by Dhaka Transport Coordination Authority, DTCA. It's a part of their project, updating the revised strategic transport plan for Dhaka that have taken a household interview survey and activity diary survey. In that survey data set, we have almost 52,000 plus households where 1.5 lakh individuals have reported their trips and which almost had 3.8 lakh data. And the duration of the survey was March to October 2023. And the type of survey was single day travel diary. The regions covered in this survey is the bigger Dhaka, that consists Dhaka, Narayanganj, Norsingdi, Gazipur, Savar, and Keranganj areas. We have spotted the maps in also here. The methodological framework of our work is we have collected the data from DTCA, and after that, data was screened. Also, we have removed the inconsistent and unsuitable records. Then the individual level data set, trip level records were converted to individual levels. And then as Dhaka consists of informal modes, so we had almost 30 modes in our data. So we have clustered them, and finally we have reported 11 modes. And also travel time allocation, we have the summed the daily travel time by mode for modal share. And the multimodality indicators were chosen, compute all indicators, and analysis was done, descriptive and regression both. And then we have tried to interpret the results. So in mode classification, we have clustered 30 modes up to 11 modes, and the 11 modes have been seen here: motorcycle, walking, three-wheeler, shared ride, private car, etc., etc. And we have mentioned one thing, that Metro Rail is grouped under transit. I am not sure whether you guys know about it or not. Metro Rail has launched in Dhaka nearly in 2023 at the end. So during the survey period, it was partially operational. So that's why we couldn't keep it as a distinct mode. We have grouped it under transit, public transit. So the transport modes, 11 modes under that, the clustered are seen here. Under motorcycle, there are self-driven, driven by friends and family, and under walking, three-wheelers. So that's the clusterization of it. After that, measuring multimodality means measuring distribution. Under it, we can see two persons and two scenarios, I mean. So here, the modal split is equal. Walking is 33.3%, rickshaw also, bus also, the same modal split. But in case of person 2, that person is more dependent on bus rather than walking and rickshaw. But still, he uses 3 of the modes. So we can say 2 people can both use 3 modes, but they are not equally multimodal. Only mode count is not enough. We also need to see how much time they're consuming in it. Also, we need continuous indicators. So indicators framework, out of it, we can see the diversity-based indicators, which explains how many different modes are used within a travel pattern. So the pure multimodality index OMPI by Diana and Mokhtarian, and also multimodal indicator MMI can capture this diversity. In case of inequality-based indicators, how equally travel is distributed across modes is captured. So Thale index, Atkinson index, Dalton index, this can capture this inequality. In case of concentration based, we can see how concentrated travel is among different modes. Herfindahl-Hirschman index can capture this. And also in case of group sensitivity, we can consider difference between groups or multiple dimensions of multimodality here by MMI. Equations of these indicators have been given here, and also regression equation we have used in our research also has been recorded here. Now, the monomodal traveling in Western countries we have found from literature is that mostly car ownership or car-dominated peoples are monomodal. But in case of Bangladesh, the scenario is different. For the monomodal group, walking is the most dominant for monomodality. Like we can see that 60% individuals uses walking. In case of multimodality people, the most used modes are rickshaw, three-wheeler, and transit. But in case of car and motorcycle, those are not much used by multimodal individuals. Then we have tried some combinations like for 2 modes, 3 modes, 4 modes, and 5 modes. And we have recorded here top 90% combinations. And we have found that walking rickshaw is the most dominant combination of 2 modes. In case of 3 modes, we can find that the walking rickshaw and transit. We can find the insight from here that to avail a transit, people need the first and last mile connectivity, which is ensured by walking and rickshaw. Also, in 4 mode and 5 mode combinations, we can see that the domination combination revolves around walking, rickshaw, three-wheeler, and transit. So these are the modes that are mostly used by the people of Dhaka. Now, the variation across groups has also been recorded here. If we see from the gender perspective, we can see that males are more multimodal than females. And in case of age group, we can see that the working age adults, like starting from 19 to age 65, they are more multimodal than other groups like children and old people. And also students and special groups show visible differences, like in Dhaka and Norshingi, the people are more multimodal than Gazipur and Naranganj. And in case of social status, self-employed peoples are seen to be more multimodal. Now, the indicators result we have found across age, gender, and other socio-demographics are reported here. So we can see that the 4 indicators here, OMPI, Herfindahl-Hirschman index, then Dalton index, and MMI. So here, when the values increases, multimodality also increases in case of the 3, OMPI, Dalton, and MMI. But in case of Herfindahl-Hirschman index, if the value increases, multimodality decreases. So we can see the trend to be similar in all the 4 indicators, and the multimodality increases from children to working age adults, then declines among older respondents. Also, in case of across personal income, we can see that the multimodality rises toward middle income groups, then weakens at the highest income category. So insight from here can be taken as highest income category people are have vehicle ownerships like car or motorcycle. So they usually use those modes, and that's why they are monomodal. And in case of very low income people, they actually choose walking as their primary mode. So that's why multimodality is seen just in between that middle income peoples. And across gender, we have already seen that males are more multimodal than females. That also has an insight like security, safety, and all in transits. So males tend to use more modes than females. Also, multimodality across vehicle ownership, we can see that CNG ownership, car ownership, motorcycle ownership, other vehicles ownership, bicycle ownership. So personal more generally reduce multimodality, and that has been seen here. and across locations. I guess it's tough for you guys to understand it because these are the locations inside Dhaka. So we can see that the central and better connected areas show higher multimodality, but a bit suburban locations have lower multimodality. Then we have gone to the regression analysis, and here also the interpretations are, we can see that all adult age groups are more multimodal than children, strongest among working ages, and also income effective positive but not linear. Middle income groups show the highest control multimodality. And then females show more concentrated modal use. That means they choose some specific modes for their daily use. And in case of driving license or car ownership, motorcycle ownership, bicycle ownership, all the ownership leads to us in one conclusion that once a personal or household vehicle is available, people rely more on that. So they get more monomodal than becoming multimodal. And after that, in case of spatial regression, Naranganj and Gazipur area people show stronger modal concentration after controls, and the local transport supply and modal integration matters here also. The higher level students show strong multimodality, likely due to independent and spatially dispersed travel. Now, the important findings we can find from this research are multimodality in Dhaka reflects both choice and constraints. Some choose monomodality by choice, some choose multimodality out of constraints. So like private vehicle ownership reduce the multimodality. People without vehicle are more multimodal due to constraints. They can't avail just only one mode for reaching their workplace or school or colleges. Conversely, very low income travelers may remain confined to walking, while middle income travelers have choice or greater mode flexibility. And also we have seen the walking and rickshaw modes as the main backbone of multimodal travel in Dhaka. It actually gives the insight of first and last mile access and improve safe walking. And modal options are unequal. Target groups with restricted alternatives improve peripheral connectivity. And the contribution of this researcher applies multiple distribution-based indicators to travel time allocation across 11 modes, shows that monomodality in Dhaka doesn't mean car dependence, rather walking and local mode dominance, which is unlikely with the Western culture or the literature we have found till now, and also identify systematic variation by demographic variables, ownership, and spatial factors. The limitations and recommendations of our studies are the data we have got from the national survey, household interview survey, that was only single day travel data. It was not 1 week or a duration data, which can give more ideas about human behavior. So ideally observe multiple days, is more ideal. Also service quality, network accessibility, and post-MRT expansion effects require further analysis. So as I have mentioned, metro was very limitedly operational during our survey period. So after that, people's mode choice changes. So that's also a limitation of our work, and assess trends in multimodal travel behavior in case of availability of future HIS survey. So that's all from my side. Thank you, everyone. And if you have any questions, we are open to it. Another author is present here.
Okay, thank you. Thank you very much. So I have a few questions. My first one is that I noticed that you have a very special mode compared with Hong Kong. I'm from Hong Kong, so which is rickshaw. So it is an expensive mode or inexpensive mode?
12 p.m.
Rickshaw. So it is a low cost mode. If I use a rickshaw, how much do I need to pay? Can you hear me? Hello, can you hear me?
Yeah, sorry, can you please repeat?
So my question is, you have a rickshaw, you have a mode, rickshaw mode.
Okay, I am going to that slide. Yeah.
So I'm not familiar with that mode. So I suppose it is not an expensive mode, it's a cheap mode, right? So I need to pay, but the money I pay is not much, right?
Which mode are you talking about?
The sixth one, rickshaw.
Rickshaw, okay, fine. Yeah, rickshaw is very much common mode for Dhaka, and here the cost is preferably low than other modes, not less than public transit, more than public transit, because rickshaw is used by only personals or individuals by own choice. So that's why rickshaw is more preferred to people because it has a reasonable value, and also people can navigate it by their own choice. Like the way or the route you want to use, you can guide the rickshaw in that way. The rickshaw puller will take you in that direction. So people prefer it more than the public transit, I think.
So even it is cheaper than taking a bus, right? It is
Sorry?
even cheap. It is even cheaper than taking a bus.
Yeah. Not cheaper than bus, but like for 1 kilometer, suppose a bus takes 10 Bangladeshi taka BDT, but a rickshaw will take around 30 to 40 BDT. So that's the difference or comparison if you want to know.
Oh, but still, the people prefer to take rickshaw. I'd be
Yeah.
surprised.
It's because you have to wait for a bus. You have to wait for the schedule of a bus and the route the bus has. You have to follow that. But in case of rickshaw, you don't need to wait for that. You can avail rickshaw in any location or in rickshaw stands anytime. And also you can you can guide the rickshaw in your preferred route. So that's a bit more flexible for a person to use rickshaw, just giving a bit more money than bus.
Yeah, because I didn't see a mode called taxi. Is there any taxi in that city?
Okay, in some places there are short water bodies or like water canals that that needs to be crossed. So we use water taxi for that. That's very rare, not in very all the locations. Suppose like in 10 or 20 places in the Dhaka city.
Okay, only water taxi, not the taxi on the street. So that's why rickshaw is similar to the purpose of a taxi.
There
Yeah.
are taxi in the shared ride.
Shared car is something different to me. Taxi, I can travel by taxi alone. The shared car is a special type of shared taxi. So I just want because I thought it's a low cost mode, but seems not. Okay. So because I saw a page, a slide, someone used rickshaw combined with other modes. Am I correct? Rickshaw first and then transit. Am I correct? Hello?
Yeah.
So what is the combination mode? It seems that I saw a page saying that some people using rickshaw and then a transit, right?
Are you talking about this one?
No, I think you have another slide talking about combination of two modes. Not this one, even later.
So basically, the transit are in the main lines.
Yeah.
Of the,
so, but they still prefer to use rickshaw to first and then transit. Yeah.
Yes.
Not this one, the previous one. Yes. I suppose you have combination of rickshaws and other modes, right?
Yeah.
What can rickshaw? I suppose rickshaw is the first mile and last mile, right?
Yeah, and also people have given the survey like this that how much time they have allocated in which modes. So we have combined those and brought it from trip level records to individual records, the total thing. So so we got the record like which people used how many modes, and from that we have made some combinations statistically, and then from there top 90% combinations has been recorded here.
So let me clarify. Do you understand my question? Do you know what is first mile, last mile?
Yeah.
So I guess from this picture, you are saying that someone used rickshaw and then transit and then rickshaw, right?
Yeah, suppose transit bus stop or metro rail stations are suppose 3 kilometer or 4 kilometer away from my home, but I need to avail that. So in that case, at least I have to walk up till getting a rickshaw, and after that, using that rickshaw, I will reach the
Oh,
bus station, and after that, reaching my destination after alighting from the bus. Then I needed to use another three-wheeler to get into my workplace like this.
oh, three-wheeler is something different from rickshaw, or they are the same. You have rickshaw, you have three-wheelers. Are they the same thing?
Three-wheelers are something like we have rickshaws are also one type of three-wheelers, but we have other three-wheelers like CNGs that needs the fuel named compressed natural gas. So, and rickshaws are driven by rickshaw pullers like manually, but in case of
Okay.
CNG and other three-wheelers, they use batteries or fuels like that.
What is the cost of using a three-wheeler then? Still the same as rickshaw?
That's faster than rickshaws, and also those are bigger in sizes, so they can be used as shared ride to 2 or 3 people can ride who are sharing their three-wheeler.
So you mean this one is cheaper than rickshaw?
Yeah.
Okay. Okay, that means in that city, the public transport is not very expensive, so that we have to use rickshaw or three-wheeler mode so that I can use transit later. Am I correct?
Yes, you were correct. Also, I
Okay, I
have
see.
told in my first introduction that Dhaka has a very fragmented service. Like the service is not very well planned or something like that. So that's why if you want trip from your house to your final destination, so you actually need to use, if you use transit, you actually need to use some other modes like rickshaw or three-wheelers for your first and last mile connectivity.
Yeah, I just want to figure because you are comparing rickshaw with walking. To me, walking, you cannot walk too fast. So you have to pay a very expensive mode then.
Yeah.
Okay, I see. Okay, so any other question? I see a question. How to tell apart the modal flexibility compared with involuntary multimodal? So can you see the question from the chat box? There is a question.
We cannot exactly tell apart, but it seems as our 60% of monomodals are taking walking, so I probably they are this is therefore involuntary multimodality, and the people who are choosing monomodality for flexibility are mostly car dependent, and they have their own car. So as the behavior pattern change from a modal constraint to modal flexibility, I think the middle people have both of them. They choose multimodality for modal flexibility, also for involuntary multimodality.
Oh, okay. So I think we run over our time. So slightly run over time because I noticed that there will not be 6 presentation anymore because the last presenter actually saying that he's not available. So we have 5 presenters, but still we slightly went over the time. So I have to stop it here. So thank you very much for your presentation. Okay.
Okay, thank you.
The 4th presenter from the Department of Roads. Are you here? The 4th presenter. Yeah, okay. Yes, okay. So could you share your screen?
Okay, I'll try. Is it visible?
Yes, I can see it.
Okay,
So
thank you.
you may start now.
Thank you. Good afternoon, everyone. I'm Prakriti Pandey. I will deliver presentation entitled Characterizing Road Surface Properties and Two-Wheeler Interaction. Here it shows are the slides changing? Sorry. Okay, here it shows the structure of my study, which follows the introduction, motivation, experiment, and conclusion. Here is the structure of today's presentation, and I will begin with the background of the study. Here I will be presenting an analysis of traffic composition and the use of ride-sharing services in Kathmandu, Nepal. As you can see from the heat map on the left, we observe that motorcycles and cars constitute the major share of traffic over the years, with motorcycles having a slight increase in their share. Moving to the right side of the slide, we see a pie chart depicting the types of vehicles used in ride-sharing services in Kathmandu. The chart shows preference over motorcycle is higher. So we can see that the traffic composition in Kathmandu is dominated by motorcycles, both in regular traffic and ride-sharing services. Contextually, our maintenance policy for the road infrastructure focuses on 4 core ideas: sustainable, safe, reliable, and user comfort. Currently, road surface maintenance thresholds are based on the International Roughness Index, IRI, to evaluate road surface quality. Road surfaces are categorized into 4 categories based on its IRIs: good, fair, poor, and bad. While this index is globally used, it was originally designed based on a simulated car model. Given the prevalence of motorcycles, particularly in developing countries like Nepal, we must ask if the IRI sufficiently reflect the comfort and safety of a two-wheeler riders. Our study tries to explore this question. To set the foundation for our study, I want to begin with an overview of road surface characteristics and roughness evaluation. IRI will be discussed multiple times in this study. So to understand IRI, it is derived from a quarter car model. The IRI is defined by this equation, which is a scale for roughness based on the simulated response of a generic motor vehicle to the roughness in a single wheel path of the road surface. The IRI is widely used because it provides a standardized measure of road roughness, which can be directly correlated with ride quality and vehicle operating cost. However, motorcycles interact with road surface very differently, especially because of their lower mass and two-wheel design. This calls into question the suitability of IRI as the sole metric in evaluating road quality in motorcycle-dominated environment. Our another point of interest is road profile. Our road profile can be presented as the sum of sinusoidal waves mathematically. The key characteristics of a profile are its wavelength, amplitude, and phase. These features help us understand the periodic nature of a surface irregularities, which is essential for analyzing vehicle-road interaction. This chart summarizes the different surface textures along with their wavelength and their impacts. Microtexture improves friction and skid resistance, while megatextures contributes negatively, increasing rolling resistance, noise, and tire damage. Thus, balancing these features is critical for optimizing safety, comfort, and operating cost. Before diving into methodology, let's look at the motivation. This diagram shows the different road surface wavelengths and how they correspond to texture types from microtexture to slope. The range that affects most ride comfort lies within 0.5 to 50 meters, commonly categorized under roughness. In this context, IRI is focused on the wavelength ranging from 1.2 to 30 meter. Now, while generic motor vehicles are primarily affected by longer wavelengths like roughness and slope, micromobilities and two-wheelers are far more sensitive to shorter wavelength, especially in the megatexture range. This mismatch is important because existing pavement evaluation tools like RI focus on vehicle models that don't capture the response of two-wheelers. So our study focuses on 2 core issues. First, understanding how motorcycles vibrate in response to road surface irregularities, and second, characterizing the specific wavelengths of road surfaces that contribute to the resonance of motorbike. Now let's look into the methodology. This slide outlines the key steps involved in our experiment design. I will be exploring in detail in subsequent slides. The 3 test roads, each of different surfaces of length 150 meters, were selected for experimental purpose. The experiment location was at Hamamatsu, Japan. The 3 test surfaces are asphalt pavement, block pavement, and asphalt pavement with manhole. We employed a low-speed profiler in our experiment to measure the profile of road surfaces at a slower pace, which ensures that the road surface characteristics such as cracks, potholes, and bumps are precisely documented. Here you can see the output from low-speed profiler. These graphs show the detailed profiles of the 3 test roads. The peaks and troughs provides us with exact locations and severity of road irregularities. The profile was then analyzed using ProVal to calculate the IRI value for each test path. The smoothest section was path 3. However, due to the presence of manholes in it, the fixed 10-meter IRI was spiked at locations of drop. The same is visible from the green-colored filtered path profile plot on the right. This is the basic experimental setup we used for data collection. We used Kiowa EDS 400A logger and accelerometers to collect acceleration data from 4 locations of scooter. The sampling interval for vertical acceleration measurement was set as 500 Hz. Here you see our primary instrumented vehicle, our scooter, equipped with various sensors to measure vibrations. The physical dimensions of the vehicle is shown here. In addition, considering the horsepower of the vehicle and safe speed at which rider can ride on road, speed of 15 km per hour and 30 km per hour were set for the measurement. 3 runs of each speed were performed on the test path as per the setup. It is the typical output from the experimental setup, which is the acceleration data for the handle and front axle of the scooter, as it plays the significant role in users' experience. From the left graph, at a lower speed of 15 km per hour, the time domain plot shows a relatively steady pattern of vibrations, indicating the response to normal road conditions. Right graphs, as we increase the speed to 30 km per hour, there's a noticeable change in the vibration patterns. The amplitude of vibration increases, and we observe more spikes. These results illustrate that higher speeds amplify the vertical accelerations experienced at both the handle and the front axle. Now let's discuss the results. In this study, we used both time domain and frequency domain analysis to evaluate road surface characteristics. Vibration data and road profile data were analyzed to determine the natural frequency of the vehicle. We did model development and its validation. This data, combined with IRI evaluation, web transform, and a road surface evaluation method was developed to verify our model. The aim was to identify a more suitable road surface evaluation index, especially tailored to two-wheelers. In order to further understand the vibration characteristics, frequency response gain was calculated using this equation. Gain is simply defined as the ratio of acceleration PST, power spectral density of the vehicle, to the PST of the road surface profile. Here you can see the typical example of gain plot. From this frequency domain analysis, we can understand that at the frequency range from 2 Hz to 10 Hz, the road to body transmissibility is amplified. Also, we understood that the gain is higher in unsprung mass. As we did the acceleration measurement from the experimental setup, we estimated the resonant frequency at which the two-wheeler vibration is high and is estimated as natural frequency of the vehicle. The next step is to estimate the parameter necessary for the vibration model of the two-wheeler. Based on the results from acceleration measurement, the sprung mass of the front wheel of the vehicle is a system with a natural frequency of 2 to 4 Hz and unsprung part to have a natural frequency of 10 Hz. And since the purpose of this study is to build a ride comfort model for vibration, we assumed it to be a 2 degree of freedom vibration model. The parameter estimation process began by calculating the mass of the sprung and unsprung part from actual measurements, and then calculating the spring constants, damping ratio, and damping coefficient to estimate the parameters. The parameters are shown in the table. Then a simulation was drawn using MATLAB Simulink to verify the reproducibility of the vibration model. The road surface profile that is first input is passed through a bandpass filter with a wavelength of 0.41 to 2.08 meter. Then the road surface profile and the estimated parameters are input into the equation of motion, and a simulation is run to calculate the mass displacement and acceleration of the vehicle as output. The figure on the right shows the result of simulation. It can be seen from the figure, the simulated acceleration has the similar spikes as the actual measured value, and it can be said that vibration model is reproducible. Next, we investigated the wavelength dominance of the road surface. The wavelength dominance of the road surface is determined by performing a continuous wavelet transform, which is a spatial wavelength analysis. In this chart, the horizontal axis shows road distance and the vertical axis shows surface wavelength, and the color intensity indicates the dominance of each wavelength. Now let's compare the wavelength dominance with acceleration experienced during test runs. We can see there is a clear relationship. The spikes in the acceleration often correspond to sections with high wavelet power, especially in the wavelength range between 0.5 to 2 meters, which aligns with the wavelength band known to affect two-wheeler ride comfort. This confirms that surface wavelength with strong dominance, those identified by this wavelet transform, are closely linked to the rider discomfort as they generate pronounced vibration responses in the scooter. Then we developed TIRI, known as two-wheeler IRI, designed based on the parameters of the scooter. Unlike the conventional IRI, TIRI aims to capture the responses that directly affect two-wheeler ride experience. On the left, we have box plot for IRI values with the average IRI marked in circles. Path 1 has the highest average IRI, followed by path 2 and path 3. These values suggest that path 3 is smoother than other two paths based on IRI. On the right, we see TIRI results which incorporate two-wheeler ride quality characteristics. Interestingly, path 3, which had the lowest IRI, now shows a higher TIRI value compared to path 2. This indicates that while path 3, which may appear smoother under IRI, but it induces more discomfort for two-wheelers, which is captured by TIRI. Looking at the frequency response of the frequency response function of the passenger car vibration model, it has maximum sensitivity at wave numbers of 0.065 per meter and 0.42 per meter. This shows that the peak position of frequency response function of 2 degree of freedom scooter vibration model are significantly different, and it can be said that it is difficult to evaluate the road surface roughness seen from the scooter using the IRI. Therefore, it became clear that the model developed in this study can be used to evaluate road surface smoothness as seen by the scooter. Now let's again compare IRI and TIRI. If we look at this graph, it also concludes that traditional IRI does not correspond to TIRI. It shows that vibration in a scooter is more sensitive than that of a generic motor. We can observe several points where the IRI and TIRI values are almost same. We can say that these points does not contain the dominant surface wavelength that significantly affect the dynamic response of the scooter. Further, the subjective evaluation of the riders can be carried out in future to find the correlation between the suitable road surface evaluation method. We identified the critical wavelength that amplify discomfort in motorcycles. The critical wavelength was found to be between 0.5 to 2 meter, which is different from that of generic motor vehicles. It is one of the objectives of the study, which we set out in the beginning. This helps bridge the gap between road surface measurements and actual user experiences. Such insights can be integrated into smarter asset management systems. In conclusion, this study has some recommendation for road asset management system. It encourages agencies to reconsider IRI thresholds or introduce complementary metrics like TRI, especially in cities with high motorcycle density. For conclusion, understanding motorbike vibration and road surface wavelength reveals that IRI alone is insufficient, and a complementary index with web-based transform provides a more holistic pavement evaluation method. This concludes my presentation. Thank you for your kind attention.
Thank you very much. So I received 2 questions from the chat box. Can you see them? There are 2 questions on the chat box.
Yes,
So
I can.
Yeah, you can answer them.
I'm curious to know how might these vibrations my devices with much smaller wheel diameter such as. Thank you for the question. Actually, even for e-scooters, while I was doing this study, my colleagues from the lab were doing on e-scooters. They were using smaller vibration measurement devices placed on the near to the handle of the e-scooters to measure the vibrations.
So I mean the main question is, if I use a different devices, still 2 wheels, but smaller or bigger, will your result highly affected by the size of the wheel?
So with smaller wheel diameters. Yeah, I think
basically the result will be affected by the size, speed,
yes,
etc. Okay, so that means your result may have some limitation you need to point out. So the result may be highly dependent on some other factor, such as the size of the wheel.
Yes,
Okay.
size of wheel, so the weight of the vehicle's physical dimensions.
Exactly. So this is the point you may need to avoid. The second question, how about the second question?
How adaptable is your break-even cost model to different environment or cities? Actually, this study is for those cities with higher number of motorcycles, especially in developing countries where the presence of motorcycle is high, but the road surface evaluation and the maintenance policies are still based on the four-wheelers perspective. It may not capture the real comfortability of the two-wheelers. So that is the purpose of this study, to develop a new system of evaluation of road surface to capture the comfort of two-wheelers. So if
that's the case, if that's the case, I suppose you need to know the percentage of each type of vehicle.
Yes. And I think it will be better to be able to provide weightage or importance factor to each kind of vehicles, or based on the type of infrastructure system, or is it a highway or a local road or that expressway, where we will give the importance factor to each kind of vehicles and carry out the maintenance activities based on that.
Thank you. So I didn't receive more questions. So thank you very much. Thank you for your presentation. The fifth presenter, are you ready? Are you here? The fifth one about the cosplay session. So
yes, I'm here. Can you hear me?
Okay. So could you share your screen? Okay.
Can you see the screen?
Yes. Could you use a full screen mode? Full screen mode. Yes. Okay. Good. So you may start.
Hello, everyone. Today, I am going to present some initial findings on my PhD research. My topic is cost-based threshold for mode shifting. It's an evidence-based break-even distance for the short distance trip. So this study explored when shifting from short car trips to walking or cycling become more economically feasible. So let me acknowledge the traditional owner of the land where Qiutina stand. And I would like to acknowledge the Department of Transport and Main Roads and the Transport Energy and Research, Emission Research as the data supporter. And I would like to acknowledge Dr. Shams Yasmin and the Professor Shimon Ha and Dr. Robin Smith for their support as a supervisor. So before moving to my research, I would like to introduce myself briefly. I completed my bachelor's and master's in Sri Lanka. Now I am a PhD student at the School of Civil and Environmental Engineering at QBeauty. So now move to the background of this study. As we all know, the transport is the sector where we can have the significant challenge such as congestion, road crashes, air pollutions, and associate health burden because of that. So when we think about the daily travel, we often talk about the longer commuter trips. But interestingly, around 40% of the car trips are short distance trips, which is the distance is less than or equal to 5 kilometers. So these short car trips are particularly important because it emit cold start emissions. It's the high proportions of emissions from the vehicle can be emit. So then, other than that, the previous study has suggested that shifting from car, if we are shifting 41% of short distance car trips to the sustainable mode, we can reduce the 5% of carbon dioxide equivalent. So another important point is most of the car short distance trips are not the work related trips. They are kind of a shopping, social and recreational type of trips. So that means there is a potential for shifting those trips from car to active transport. So if we can shift these trips to active transportation, we can have both environmental and health benefit. That's why I have focused short distance trip in this study. So then, if we are saying that there is that much of potential for a model shift for a short distance trips, the next question we should ask is why do people still choose to drive? Not every car trips can realistically be shifted to the active transportation because there are some restrictions. As an example, we can say there is a distance which we cannot use the active transport, and if they are carrying heavy good or their children, we cannot ask them to use active transport. So that's as this, we have several constraints. So because of that, we cannot say all short distance car trips can be shifted to active transport. So the important question is, what is the optimum point of shift and what distance does the walking and cycling become more cost effective than driving? So this is the main motivations of this study. To identify this, I have considered the feasible distance threshold for shifting from car to active transport. So it gives me the economical feasible distance threshold. So how do we identify this optimal point of the model shift? In this study, I use the concept of break-even distance. That distance represents the switching point which driving to the sustainable mode become more cost-effective. To estimate this distance point, I have used the generalized cost, which combine both monetary and the non-monetary components. So other than that, I have used the mode choice model to understand how individual travel decisions are taken, and the parameter derived from the mode choice model I have used to estimate the generalized cost as well. So ultimately, the purpose of identifying these break-even distance is to suppose the practical solution for the model shift. So by understanding where the walking and cycling become competitive with the driving, policymaker can better target the intervention to reduce the emission and improve the public health as well. So Based on this motivation, the main aim of this study is to examine the mode shift potential of short distance trips using the generalized cost and break-even distance. To achieve this, I have focused three main questions. First one is what are the factors influencing the mode choice for short distance trip? The second one is how does the travel distance affect generalized cost and the potential for emission reduction? So the third one is at what distance that shifting from driving to walking or cycling become cost effective. So for this research, to address these research questions, I have developed the main hypothesis of the study. It is the lower generalized cost of sustainable mode will increase the likelihood of mode shift from car to sustainable travel mode. And to conduct this study, I have chosen the Southeast Queensland as the study area in Australia. And my study period is 2021-22 financial year to 23-24 financial year. The unit of analysis is the short distance trips. That means the distance is less than or equal to 5 kilometers for the car travel. And this study has integrated several databases. Mainly, this has include the household travel survey data. That data provide the mainly trip and the travel informations. And it has incorporated with the Hongtai accessibility measurements, transport infrastructure, roadway and land use data. And so this data provide the various socio-demographic and economical characteristics. So other than that, for a level of service measurement such as travel time, travel distance, and travel cost, I have used the Southeast Queensland strategic transport model. For the emission calculation, the emission factor and the cost emission factors obtained from the literature based on the Australia. So this slide show us how the sample size is determined. For, as I explained earlier, my sample is consist of the short distance trip, which is the car travel distance is less than or equal to 5 kilometers. And I have targeted only the people who have age is more than 16 years or above, because they are the independent travel decision makers. And I have considered the 80-20 rule to sort out, select the estimated sample size. And then this graph shows the distributions of the dependent variable. Mainly I have 6 dependent variables: car driver, car passenger, public transport, bicycle, walking, and other mode. So as you can see, even though this is the short distance trip, predominantly that means 64% of trips are car drivers. And for the active transport, we have the very limited portions for a walking 19% and for a bicycle only 2%. So these are the steps which I have followed for this study. First, I have estimated the mode choice model, and then it helps me to identify the factor influencing the traveler's mode choice model. And then I estimate the those estimated parameters I have used to construct the generalized cost function, and then I estimate the break-even distance between car travel and the active travel mode. Finally, those results used to explore the policy implications and potential model shift. So here for the mode choice model, I have used the multinomial logic model. This is the utility and the probability functions which I have considered in my model estimations. So Yuen is the utility across the different alternative by the different individual n, and Vni represent the observed utility of the utility functions, and for calculating the probability of selecting each mode has considered by optimizing the maximum likelihood function. And here for the travel time and travel cost, I have considered the generic coefficients, assuming their marginal impact is same across all modes. So this slide represents only a few key variables. I did not present all the variables here. So those variables I have included in my generalized cost calculations as well. So in that slide, you can see as expected for the travel time and travel cost, I have obtained the negative coefficients. That means it indicates the increasing travel time and travel cost reduce the attractiveness of the alternative. And for the infrastructure variable, you can see for a busway density, walkway density, and ferry stop availability show the positive effect on the walking and public transport that highlight the importance of supportive transport infrastructure. And other than that, we can see the motorway density positively influence on the car passenger choice as well. So in the last variable, you can see the average accessibility time to destination. That variable I have considered as the area level impedance value. So that variable also shows the negative impact and that indicate if the accessibility is poor, that represent the longer accessibility time to destinations. That means it increased the level of impedance associated with the travel. So these estimated parameters are then incorporated into the generalized cost function and to represent the monetary and the non-monetary impedance of each mode. Before constructing the generalized cost function, I followed the framework proposed by the Goodwin in 1978. So according to his framework, the component in the generalized cost should represent something that traveler expend during their journey, and that can be the objective measurement, and it does not generate any benefit, or a traveler should also prefer to minimize this expenditure and able to get the trade-off between those attributes. So based on this principle, I evaluate which are the variables I should consider from out of the mode choice model to generate the generalized cost function. So then I have considered, based on the Goodwin's criteria, I have considered 4 variables. Those are the travel cost, travel time, average accessibility time to services as the area level impedance, and the emission cost. So this variable represent the measurable expenditure and the impedance associated with each trip maker. So then to calculate the generalized cost, it include both monetary and the non-monetary component of the trip. So I have to convert non-monetary component into the monetary component. To convert travel time, I have used the value of time. And for other friction variable, I have considered the cost sensitivity parameters. So then in the next slide, I will show you the equations which I have used to calculate the value of time. So first equation is the equation which I have used to calculate the value of time, and then the second one is the cost sensitivity parameter which I have used to convert the accessibility area level accessibility component into the monetary component. So in this analysis, I obtained the value of travel time as the $90.26 per hour, which is matching the existing literature in the Australia. So then, other than that, I have to consider the emission cost as well. That emission cost value I have obtained considering 3 parameters. One is the travel distance. That value I obtained from the Southeast Queensland strategic transport model, and the average emission factor and the emission cost factor I obtained from the existing Australian literature. So using this generalized cost component, I developed the 3 scenarios to examine how accessibility and emission cost internalization affect the break-even distance. The first one is the business as usual scenario. It consider only the travel time and the travel cost. And the second one, I add the average accessibility time to different services to examine how accessibility condition affect the relative cost of driving to the walking and cycling. In the third scenario, I add the emission cost of car travel to examine whether internalizing the external cost change the attractiveness of the active transport related to driving. So then I will present the comparison between each scenario. The first one is showing us the accessibility change, the break-even distance between driving and the walking. Here we can see the break-even distance represent the point where the generalized cost of the walking become equal to the generalized cost of driving. So under the business as usual scenario, the break-even distance is approximately 660 meters. So when we add in the average accessibility time in the area, it reduces the break-even distance up to 420 meters. That means there is a 240 meter reduction. So it indicates that accessibility condition can sustainably influence the relative cost effectiveness of the walking compared with the driving. Under the average condition, this represents here the walking become cost effective relative to the driving at a shorter distance once accessibility considered. So then same thing I have done with the cycling as well. So here also we can see for a business as usual scenario, the break-even distance between cycling and driving is approximately 8.31 kilometers. That means after adding the average accessibility time, that distance has decreased approximately 7.4 kilometers. That means there is a 900 meter reduction. So this again demonstrates that the accessibility condition have an important influence on the relative generalized cost of the active transport, with even the larger absolute change in the cycling. So now I have examined the effect of the internalizations of emission cost of the car travel. For a walk-in, actually, the break-even distance is same for both scenario. That means it is after adding the emission cost also, the break-even distance becomes the 660 meter. That indicate the internalizing emission cost has the negligible influence on the relative cost effectiveness of walking for a short distance trip. So therefore, for a walking, the results suggest that the improving accessibility and infrastructure may be more influential than the imposing additional cost to car travel. And for a cycling, actually, under the business as usual scenario, we have the break-even distance as the 8.31 kilometer. After adding the emission cost to car travel, that break-even distance has increased by 500 meters and it has become 8.82 kilometers. So that means after adding the emission cost, make driving relatively more expensive and therefore extend the distance over which cycling is cost effective compared to the driving. So, however, the magnitude of this change is relatively small and suggests that the emission cost internalization has only the marginal influence of the cycling compared to the effect of accessibility improvements. So, after considering all these things, as a conclusion, I can say for the estimated break-even distance range for a cycling is for a walking is in between 420 to 660, and for a cycling it is from 7.7 8.4 to 8.8 kilometers. So under the different scenario, we have these values, but by considering this finding, we can say the better accessibility reduces the break-even distance. It shows that the accessibility and the supportive infrastructure facility can reduce the burden associated with the active travel. And in comparison with the internalization of emission cost has the negligible impact for a walk-in, and there is a marginal impact for a cycle. So this suggests that particular for the short distance trip, improving infrastructure and accessibility may be more effective than imposing additional penalty on car users. So therefore, the short-term priority should be to improve walking, cycling infrastructure like public transport accessibility, active travel awareness program, and this access and improvement for the access to essential services within the short distance. Those type of policy implications can be done for a short distance trip. So the main message in this study is we can encourage modal shift by making sustainable mode easier and more accessible rather than simply making car travel more expensive. So for the future research, actually in this study, I have considered the average generalized cost and the break-even distance by considering users as a homogeneous, but actually the travelers are heterogeneous and their preference and sensitivity is different. For as my next study, actually I am going to estimate the individual level is generalized cost and the break-even distance. It helped me to capture the user heterogeneity. So then those findings will help me more to suggest more realistic policy implications. Thank you very much for your attention. And if you have any questions, you can ask now.
Thank you. Thank you very much. So if you have questions, you can type it in the chat box. I have my first question here. So my understanding, you calculate the break-even distance, assuming certain environment. So am I correct that you collect the data based on a sunny day
Could you repeat the question again?
So did you collect the data to calculate break-even distance? So I suppose you collect the data, right? How to calculate?
I actually consider the existing data. I am using the secondary data, that the household travel survey data and the available infrastructure facility and the Luktai data from the accessibility measurements. Those are the existing data. I use those existing data to model.
Yeah, so my concern is when they collect the data, did they specify the temperature, whether the day is sunny or rainy? Because the cycle
no, actually, that is the limitations of the data.
Okay.
We don't have that information.
And if immediately there may be snows, then I think that may affect the mode choice. No matter what, even just
your suggestion is actually correct. It impact on especially for the active travel, but the limitation is in our current data set, we don't have any information regarding that.
Okay, so for active transport, you only consider cycling. You haven't considered other active transport like e-scooter.
E-scooter proportion is very limited actually. It is even though in the cycling also it's only 2%. That e-scooter one is less than 1% actually. That's why I couldn't consider that one as the separate alternative.
Okay, so because when you talk about cycling, there are actually two types. One is private. You own your own bicycle. The second one is public. You use a share bike sharing system. So the data didn't differentiate that much.
Yeah, those the more proportion is very less. That's why I combine all of the taxi and the shared scooter and e-scooter, all of them as the other mode, because their proportion is very less compared to the other modes. So if I consider them as a separate alternative, then the model estimation is not overestimate or underestimate.
Okay. Okay, thank you. So I didn't see other questions from the chat box. So thank you. Thank you very much for your presentation. Thank you. I think this is the last presentation because the sixth presenter is not available. Thank you all for joining this section. Thank you very
Hello.
much. Yes. Are you
Yeah,
here?
I'm here. I am here. But
Someone said that you are not here. This last
yeah. I am at my workplace right now, and I got my recordings with me. Can I play the recordings of my presentation?
Yeah. You can still
I
talk.
can. Oh, thank you so much. Thank you so much.
Okay.
I'm currently sharing.
But you only have limited time because I suppose you are not available. Okay.
Yeah, I wasn't available, and my co-author is also not available because he got a load shedding in his area, so that's why.
Okay. So, okay. Luckily, this is the last section. Okay. Okay. So you can share your screen.
The screen is visible.
Yes, now I can see.
Yeah. Okay, then I'm playing my recordings. It's actually a pre-recorded presentation.
Okay.
So I'm playing it. Thank you so much, Sarkar. And today I'm going to present my work named Integrating Crowd Shipping with Urban Metro Systems, Evidence from Dhaka using Discrete Choice Modeling. And my co-authors are Trina Shah and Mohammad Niaz Morshed. So the first question arises here is, what is crowd shipping? So if I'm going to answer what is crowd shipping, then the first thing I have to say is we will use the regular commuters to deliver the parcels from one place to another. Like whenever a person is moving to his destination, then he will just carry a parcel, and before going to his destination, he will just deliver the parcel to its destination, and then he will just continue his movement. So it will reduces the cost, and it will also improve the last mile logistics. So why it is important? So it will reduce the traffic congestion and delivery costs. How? As the amount of trips will get reduced here, so it will also reduces the traffic congestion. And how it will reduce the delivery costs? So in our country, in Bangladesh, Daraz and other company who is actually delivering the products have a minimum 70 Bangladeshi taka, minimum 70 taka or like 60 or 80 takas. But in my work, the maximum amount of payment is 50 takas. So obviously it is lower than the other amounts that we can see in other delivery services. So obviously it will reduce the delivery costs also. It will also support the sustainable urban mobility, and obviously it will offer some extra income for the participants. And in Dhaka, crowd shipping is not available, and no prior research work is also found. So it's a completely new concept in Dhaka, and so it has a potential to integrate the crowd shipping with daily commutes. So what is the main problem? So there is a clear knowledge gap, and we have to understand the willingness of participation, the willingness of participation of the people. So people's willingness mainly depends on payment, parcel size, and distance. Obviously, there will be some more parameters, but there are no clear model exist to determine the fair compensation level. And for in our country, there is no prior research, and also crowd shipping is not applied anywhere in the country, and that's why it's not actually possible to find any data to review. So we have to do a stated preference survey here. So there is no clear model. Lower wages may affect the willingness, and without proper insight, crowd shipping may fail. So that's why it is a clear knowledge gap, and we have to find the right balance between the cost and compensation. So why we need the study? We have to optimize the incentives, and Metro Rail opens new opportunities for parcel movement, as it's a new concept in our city, and it creates a fast delivery method. So our study contributes in several sectors, like we can identify the impact of payment, distance, and parcel size. It also analyzes the demographic influences like age, gender, income, etc. and it also helps the policymakers to design better systems. So there are some objectives, like we will develop a binary logic model to quantify the factors, and the key determinants like payment distance, parcel size, they will get identified here. Also, we will analyze the impact of monetary compensation and some demographic effects. Finally, we will find out the thresholds for parcel size and distance, and we will give some a policy recommendation. So methodology overview. We will use a binary logistic regression in R. So we have created a Microsoft form, and we have collected data from 393 respondents. And for analysis, we got McFadden's R-square value, log likelihood ratio, p-value, z-test, elasticity, trade-off, and marginal effects. So what are the variables? We can see the main independent variables are payment, parcel size, and distance. We got some demographic variables like age, gender, education, and income. And finally, the dependent variable is the willingness to accept. So it's a yes or no question. He will answer whether he will accept the delivery or not. So survey setup. There are 6 scenarios. Each scenarios have different parcel size and different distance and different payment levels. So each participants will have 6 scenarios, and they will have 3 questions per scenarios. So total 18 questions will appear, and 393 respondents and 18 questions. So total 2,358 total observations are here. So the tool is used here is Microsoft Forms. So the choice experiment type is a binary choice experiment. We can see from the table there is a scenario description. The participant is requested to deliver a small parcel size. Small parcel. The size is like a card deck size, 2.6 inch, 3.6 inch, and 0.75 inch. And the distance is to a location within 500 meters of the road, approximately 5 to 7 minutes of walk, in exchange for a payment of 15 BDT. So this is the scenario, and the question is, will he accept the delivery for 15 taka? Then he will give his response using yes or no. So the answer is between only yes and no, and that's why we have chose binary choice experiment for this work. So there are the 6 scenarios. The parcel size small, medium, and large, and the distance range from within 500 meter and 500 meter to 1 kilometer. And we have provided 3 payment options for each scenario. So 6 multiplied by 3 is 18. So also payment decreases with parcel size and distance, and it will also ensure the logical decision making scenarios for respondent. So then the data is processed and encoded using some parameters like 0, 1, 2, 3. Age, so 18 to 25 is 0, 26 to 35 is 1, and so on. For gender, female is 0, male is 1. For education levels below, class 8 is 0 to 5, masters and PhD. For income also, less than 25,000 is 0, and 25,000 to 50,000 is 1, and so on. For parcel size, the small parcel size is 0, medium parcel size is 1, and the largest parcel size is 2. And for distance, less than 500 meter is 0, and 500 meter to 1 kilometer is 1. So this is the methodology. So there are some assumptions here, like observations are totally independent, no perfect multi-core linearity between them, and a logic relationship between the variables. And for evaluation, we have used the McFadden's R-square value. For variable significance, we have used p-values, and model significance, the log likelihood ratio test. So let's see the result. So we can see there are some estimates which is negative and which are some positive. Positive coefficients means the willingness is increasing, and for negative coefficient, it means the willingness is decreasing. And for p-value less than 0.05 means it's significant, and more than 0.05 means it's non-significant. So let's see. Age is negative 0.11, so it has a negative coefficient, so decreasing the willingness. For gender, it's 0.137, positive, but there is a catch. The p-value is 0.08, which is greater than 0.05, so it's not a significant variable. For education, it's 0.069, positive, and income is negative 0.33. So if income increases, people's willingness decreases. And for education, it's positive, so more educated people, so like the people are more educated, then they will have higher chance to accept the delivery. For parcel size and distance, it's very strong, and negative 1.33 and negative 2.32. So those variables are very strong, and they have negative influences. So if parcel size gets increased and the distance gets increased, the willingness to accept will reduce. And we can see those parameters are also significant. For payment, it's positive 0.18. So if payments gets increased, it will also make people accept easily. And we can see the values of z-test is here, and the p-values are also here. From that we can see everything is significant, only gender is the non-significant parameter here. So the McFadden's R-square value, we found that is 0.213, which means the predictive power is quite good. Log likelihood ratio is 1,852. So we can see the model significantly better than the null model, and only one insignificant parameter is here. So what are the key takeaways? Higher payment means more willingness, as the coefficient is positive. For distance and parcel size, if it gets larger, the willingness will be lower, so they have negative. Higher income respondents.
Apologies, Ananta, we are running out of time. If you wrap up, I would appreciate. Thank you.
Gender doesn't have any significant influence here. So here are the graphical influences. So the coefficient estimates, we can see the distance has the lowest amount of coefficient is negative 2.5, and then the parcel size has the second lowest, and then income, age, and we can see some positive values also. Education and gender is positive, but in previous slides we saw that gender has no significant influence. Predictive probability versus payment, we can see if payment is payment increased here, the probability also increases with payment. For parcel size, if parcel size gets larger, it will reduce the probability of acceptance. Same goes for the distance. If we increase the distance, the probability reduces significantly. For gender, we can see females have lower probability of accept than a male, but this parameter is not significant. For age, we see the middle-aged people have higher probability of acceptance, like the age group of 1 means 15 to 24 years.
Ananta, can you skip some of the slides, please?
We can see the probabilities are almost equal. It is pre-recorded, and that's why I have make the speed faster, so it will be end within 3 minutes. For education level, we see the higher education levels have more chance to accept. Lower education level peoples do not like this method at all, but it's also very weak. For income, we can see a clear straight downward movement. If income gets increased, the probability reduces from almost 0.8 to 0.5. So it's a huge drop. And then the elasticity trade-off and marginal effect. So we can see the elasticity effect, payment is positive, parcel size is negative, and distance is negative. And between parcel size and distance, parcel size has more lower value, like negative 0.5. Same we can see from the marginal effect. From compensation trade-off, distance and payment is 12.8 BDD. So if distance is increased by one value, we have to increase the payment by 12.8 taka. For parcel size, it's lower, but it's still high like 7.36. It's lower than distance payment trade-off, but still it is a significant value of 7.36 taka. So if we increase the parcel size by one value or 1 point, so it will we have to provide 7.36 taka more to compensate. So we can see payment motivates the participation, but distance and parcel size determine how much compensation is required. So in conclusion, I have to say that payment, parcel size, and distance significantly influence the crowdsourcing participation. Higher payment increases willingness, but larger parcel and longer distances decrease it. Then we can see the income has a considerable high impact on decisions among the demographic variables, while age and education have significant but weaker impact. And only the one demographic variable, which is gender, is the only insignificant parameter here. There's some limitations here, like the location and demographic values are very limited, and the delivery scenarios and the payment are also fixed. We have also explored some external factors like weather, time, traffic, and the logistic regression method is very basic here. As we can see, you will have to say that the values are the data I have collected is a panel data, as one person have 18 separate answers, and everyone, like 393 respondents, have 18 answers each. So this model is very basic here. So why have you used basic model? Actually, in Bangladesh, there are no prior work is done, so the literature is very limited, and that's why I have created a basic model just to create a baseline so that I can use them, or I can use the help to make some advanced model in future, like mixed logic model or multinomial logic model. Lacks behavioral insight like trust, risk perception, and the study has no long time trends. As I said prior, that no previous literature is found in Bangladesh perspective. It's completely new work. Is new work here, and no metro variable used. Metro rail related variables are not here. So some recommendations, like we can expand it to diverse region. We can implement dynamic pricing and real-time scenarios, as it is very fixed in my work. And we can use some external factors, and also we can include some behavioral insight beyond payment. We can use some advanced models using this as a baseline. We can conduct longitudinal research on trends, and also we can use some metro variables like station access, transfers, and lockers, crowding, etc. Thank you. This is my presentation, and I hope my presentation provides you enough insights about my work. Thank you, everyone. And that's all from my side, actually.
Well, thank you. I think we are running out of time, so it is better to end this section. Thank you all for joining this section. Thank you very much.